Hello, welcome to the first week of the pre-university calculus course. Do you remember this from our course promotion video?
The World Solar Challenge. A race for cars using only solar power to cross Australia. Racing 3,000 kilometers from Darwin to Adelaide. Students of the Delft University of Technology built the Nuna 7 and won this World Championship of solar cars. How are mathematics like calculus important to building a winning car?
The students of the Nuance Solar team have a clear challenge. Design a solar car that can drive the long distance as fast as possible using only the sun as a power source. This is what we would call a real-world problem. In terms of energy, you want to build a car that maximizes power input and minimizes power loss.
The first step with such a problem or challenge is analysis. You try to break down the question in smaller and more specific questions like how much power can you harvest from the sun? What is the influence of power losses like air friction, roll friction and battery loss? Here starts the modeling cycle that is used in science, design and engineering. You have a real-world problem and you try to reformulate it in terms of a mathematical model. A mathematical model describes the relation between the different parameters that are of influence in this real-world problem. Such relations are described by mathematical functions. Just a small example of such relations. The power input of the Nuna car is described by a function relating the efficiency of the solar cells, the area of the solar cells, the height of the sun and other quantities. Power loss depends on roll and air friction, which both depend on speed and other parameters, and loss of electrical power. Once you modeled your problem in terms of functions, you can start making calculations. This often involves solving equations, in particular if you try to find an optimal situation. For example, what is the highest speed the Nuna car can attain given certain weather conditions? After solving the mathematical questions, you have to interpret the results to predict how a design or phenomenon will work in real life. And ultimately, you will have to test your predictions and see whether they are correct or whether you need another or more refined model.
This cycle of mathematical modeling is used in medicine, economics, science and engineering to tackle real-world problems. Think of questions like, what is the optimum dose for this medicine? How can you maximize the profit of your company? How can you design a thrilling roller coaster ride? How can you reduce energy consumption?
In particular, it shows how important it is to have a thorough understanding of mathematics if you want to be a scientist or engineer. This starts with the understanding of the building blocks of any model, mathematical functions.
In the first 2 weeks of this course, we will review the standard functions like polynomials, exponential functions and trigonometric functions. You will have lots of opportunity to practice with these functions, their properties and their applications. Have fun!
Welcome back. In the previous video, we pictured functions as machines that produce a certain output given an input. Remember that we only consider functions that send numbers to numbers. A natural question is, given a function, how to describe what it does to the possible inputs. The most common way to do this is by means of a formula. Take, for example, the square function that sends any number to its square. I guess you know how to describe this function by a formula. If we represent the input by the symbol x, then the output is x squared. We call x the variable and x squared is the formula that describes the function. How to denote such a function? First, we have to give the function a name. A standard name is f. One way to denote this function is f colon x to x squared. Here f denotes the function name, x is the variable denoting the input, and x squared is the formula that describes the output. Another common way to denote a function is by writing fx equal to x squared. Sometimes you may even hear the function x squared, although this is a bit sloppy. The power of a description in terms of a formula is that it is clear what the function does for all possible inputs. but there are also drawbacks. For functions that arise in practice, it's often difficult, impossible, or senseless to give a describing formula. Just a simple example. Think of a car racing on a track. For every lap, you can measure its lap time and put it in a table. This table then completely describes the function that associates to each lap number its corresponding time. You could try to find a formula for this, but this makes little sense. The table contains all information. A table is a convenient way to summarize dependence between quantities obtained from measurement data. For example, if you measure the world population every 5 years, from 1990 to 2010, this can be nicely summarized in a table. The problem is that you can only adopt finitely many possible inputs. More explicitly, think again of the square function. You can make a table for this function, adopting a number of possible input values and corresponding output values, but this table does not make clear what happens for other input values. It's a very incomplete description of the function. This problem is partially solved by another common way to represent functions, by means of a graph. You've probably already seen a lot of graphs in your life, but for completeness, let me remind you how a graph corresponds to a function. The points on the horizontal axis represent the input values. If you pick one, then the corresponding output value is the vertical displacement from that point to the graph. For example, we see from the graph that f1 equals -3. In a graph you can represent much more information on a function than in a table. Of course, you cannot make a graph of the whole real line, but often you do not need the full real line to capture the interesting behavior of a function. Another advantage of a graph is that it clearly shows properties of the function, like where is it increasing or decreasing, where does it change rapidly, where slowly, and where are the extrema. You can get this information from a formula or table as well, but you may have to do a lot of work. For example, I can give you the formula for this particular graph, but you may have a hard time to determine the function's behavior from this formula. In a graph, you can just see it. However, a drawback of graphs over formulas or tables is that it's hard to find exact values. Finally, a way to describe a function is just in words. For example, let's consider the so-called floor function. If I want to explain to you what it is, I can write a formula. In this case, it does not tell you anything unless you know what it's meant. I could give you a table with some input values and output values, or give a graph, but they are both incomplete. It may still be unclear what the function does. This may become much clearer if I tell you in words what it does. Putting a number x into the floor function gives you the largest integer smaller than or equal to x. I hope that now the graph and the table make sense. The formula that I wrote is simply a special notation for this function. Let me summarize. We have seen 4 ways to describe a function: by means of a formula, a table, a graph, and in words. It's very useful and important to be able to switch between these 4 ways to describe a function, especially when it comes to the standard functions that we deal with in this course. Do not only focus on the formula and its properties, but make sure you also know what the graph looks like, that you can read tables, and that you can describe the behavior and properties of the function in words. Hi. You probably know calculators like this one. If you look at the buttons, you see that it can evaluate a lot of functions that you're familiar with. But if you zoom in on the electronics behind these buttons, you will find that at a very elementary level it can only perform 2 mathematical operations exactly: addition and multiplication. This may seem very limited, but using only these, there is already a large class of functions that you can construct, the so-called polynomial functions. To be more precise, polynomial functions are functions that can be constructed from a variable and a set of numbers using only addition and multiplication. Let's look at an example. Suppose our function takes x as input. We can raise it to the 5th power, since this is just repeated multiplication, then add -1, multiply by 2x plus 3, and then finally add 1/2 times x. This is an example of a polynomial function. The expression that defines the function is called a polynomial. The expression looks a bit messy. There's a standard way to simplify polynomials. How does this work? First, get rid of the brackets by expanding the product. Remember how to do this. You take all possible products of terms in the first factor with the terms in the second factor and then add those products. So in this case, you get 4 terms from the expansion, and the term 1/2 times x was already there. After this, combine the terms with the same power of x. And finally, make sure that the terms are ordered from highest power to lowest power. This is already the case in the last expression. The final expression that we found is called the standard form of this polynomial. In general, the standard form of a polynomial looks like this: a sum of terms, and each term is a product of a number and x raised to some integer power. The terms are ordered from high power to low. Note that the powers of x are positive integers. Division by x is not allowed. The a's are called the coefficients. These coefficients can also be negative and can also be fractions. In fact, they can be any real number. A polynomial can always be put into standard form by following the simplification procedure that I sketched earlier. Get rid of brackets, gather the terms with the same power of x, and order the terms from high power to low power. An important property of a polynomial is its degree. It is defined as the highest power that occurs in the standard form. Be aware, you have to look at the standard form. For example, the expression on the screen is a polynomial that's not in standard form. What is its degree? You might say 6, since that's the highest power that occurs, but that's not correct. First, rewrite it to standard form. If you simplify, you find that the terms containing x to the power 6 cancel. The highest occurring power is 5, so that's the degree. I invite you to check the calculation yourself. Why is the degree so important? One answer is that it provides information about the behavior of a polynomial function when x becomes large. For example, consider the polynomial function px equal to 2 times x cubed plus 8 times x squared minus 13x. You can see in the table that as x grows larger, the first term grows fastest. For x very large, the first term will be much larger than the other terms. So then the function roughly behaves as 2 times x cubed, which is a power function. That is, the relative difference becomes very small. In a similar way, when x becomes much smaller than 0, the relative difference between px and 2x cubed also becomes very small. In general, we have the following. Given some polynomial function of degree n, then for x values much larger than 0 or much smaller than 0, it will be roughly equal to the power function an times x to the power n. The exponent of this power function is precisely the degree of the polynomial. In the next video, you will learn more about the relation between the degree of a polynomial and its behavior. Let me end with a final remark on the calculator that I started with. Given the basic mathematical operations that it can perform, addition and multiplication, it follows that a calculator is very good at evaluating polynomial functions. But most calculators can do much more. There are buttons for sine and cosine, logarithms, square roots, etc. How can a calculator evaluate those? And the answer is, it cannot. But using polynomials, these functions can be approximated. More about that in the university preview of this week. Welcome back. In this video, we will focus on the shape of graphs of polynomial functions. In practice, you will most often work with polynomials of degree 2 and lower. Let us look at those separately. The easiest non-zero polynomial functions are those of degree 0. Is that possible? Yes, we can write these functions as px equal to a times x to the power 0. Now remember that x to the power 0 is just 1, so these are just constant functions. The graphs of these functions are simply horizontal lines. Let's make this a bit more exciting by passing to degree 1. Degree 1 polynomials have the form px equal to ax plus b, where a and b are constants. The graph of a degree 1 polynomial function is a straight line, and that's why these functions are also called linear functions. By the way, also constant functions are examples of linear functions. If you consider the graph, the coefficients a and b actually have a meaning. A represents the increase of the function value if x increases by 1. As such, it is a measure for the steepness of the graph, called the slope. B is precisely the height of the intersection point of the graph and the vertical axis. It's called the y-intercept. For example, let's look at the graph of the linear function px equal to -1/2 x plus 2. Indeed, you see from the graph that the slope equals -1/2 and the y-intercept equals 2. It's surprising how many dependencies between everyday quantities can be modeled by linear functions. You will see examples of such dependencies in the exercises. Okay, let's go 1 degree up to functions of degree 2. These are called quadratic functions. They occur in many applications. For example, if you throw a ball, both the height as a function of time and the trajectory of the ball can be well described by quadratic functions. A very different example is the main cable of a suspension bridge, such as the Golden Gate Bridge in San Francisco. In many cases, the shape of these cables can be approximated by a quadratic function. The standard form of a quadratic function is px equal to a times x squared plus bx plus c, where a, b and c are constants. Let's have a look at the graph of such functions. The shape of the graph of any quadratic function is a parabola. It has precisely one extremum, called the vertex, and it is symmetric in the vertical line through this vertex. The relation between the coefficients a, b and c on the one hand and the shape of the graph on the other is not as clear as in the case of linear functions. However, we can at least say the following. A is a measure for the wideness and orientation of the parabola. If a is positive, the parabola opens upward. If it is negative, it opens downward. Also, the closer a to 0, the wider the parabola. Furthermore, the x-coordinate of the vertex of the parabola is located at x equal to -b divided by 2a. And finally, c again gives the y-intercept of the graph. Let me show you an example. Px equal to 1/2 times x squared minus 3x plus 5/2. Indeed, you see that the graph opens upward. The x-coordinate of the vertex equals -b/2a and the y-intercept equals the constant term. As we mentioned, you can write any polynomial in standard form. But when it comes to quadratic polynomials, there are at least 2 other forms that are also very useful. The first is the factorized form, a times x minus p times x minus q, where a, p and q are constants. The advantage of this form is that it tells you a lot about the shape of the graph. A again gives information about the wideness of the parabola and whether it opens upward or downward. P and Q are precisely the x-coordinates of intersection points with the horizontal axis. The polynomial function in our example can be rewritten as 1/2 times x minus 1 times x minus 5. Indeed, you see that the graph intersects the horizontal axis in x equal to 1 and x equal to 5. Another common form is the complete square form, a times x minus r squared plus s, where a, r and s are constants. Here a plays the same role as before, but also r and s have a clear interpretation. They are the x and y coordinate of the vertex. Our example polynomial can also be written in this form, 1/2 times x minus 3 squared minus 2. And indeed, you see that the vertex is located at 3, minus 2. What about polynomial functions of higher degree? Of course, there's always a relation between the coefficients of the and the shape of the graph, but this relation becomes more complicated and obscure the higher the degree gets. We can say some general things though. It turns out that the degree is a measure of how complicated a polynomial function and its graph can be. In fact, the following is true. If you look at the graph of a polynomial function of degree n, then any straight line will intersect this graph in at most n points. For example, in the picture you see the graph of a degree 4 polynomial function. Looking at several straight lines, you see that none of them intersect the graph in more than 4 points. Intuitively, you can think of it as follows. The higher the degree, the more wobbly the polynomial function may behave. Since you will encounter polynomial functions in many situations, especially linear and quadratic functions, it's very important to get a feeling for the relation between a polynomial and the shape of its graph. The exercises that follow this video will give you the opportunity to practice this. Good luck!
Hello. The quotient of two quantities is called their ratio. A rational function is the quotient or ratio of two polynomials. Let us look at an example. Suppose my trip to work involves 3 kilometers of city traffic, which always takes me 6 minutes, which is 1/10 of an hour. Subsequently, I have to drive 20 kilometers on the freeway with a speed v, which depends on the amount of traffic. Thus, the time on the freeway is 20 kilometers over v. What will be my average speed? Well, it is total distance divided by total time. The distance is 23 kilometers, the time spent is 1/10 of an hour for the city part and 20 over v for the part on the freeway. Thus, the average speed is 23 over 1/10 plus 20 over v. Multiplying both numerator and denominator by v, we obtain 23v over 1/10 v plus 20. This rational function is a quotient of two linear polynomials. In general, rational functions are precisely those functions you can make with a variable, numbers, addition, multiplication, and division. These functions can all be written as a fraction p over q, where p and q are polynomials. Of course, q cannot be the polynomial which is always 0. Note that constant functions are also polynomials. So, by taking the denominator to be the constant polynomial q equals 1, we see that any polynomial is also a rational function. Of course, those are not the rational functions that interest us in this video. You do get functions we could not define before, even in the simple cases where the numerator is constant, or the denominator is just a power of x. Note that we cannot define a rational function at a point x where the denominator equals 0. This means that the zeros of the denominator are not in the domain of the function. You can calculate with rational functions just as you are used to with ordinary fractions. In particular, if you want to write a sum of two rational functions as a single fraction, you have to put both terms over a common denominator. For example, if we add 1 over x minus 2 plus 1 over x squared plus 2, we use x minus 2 times x squared plus 2 as a common denominator. The result is x squared plus x over x minus 2 times x squared plus 2. Typically, factored expressions are easier to work with, so refrain from expanding the denominator unless you have a good reason to expand. In general, it is not easy to draw the graph of a rational function. A characteristic feature of graphs of rational functions are the asymptotes. For example, the function 2x squared plus 2x minus 1 over x squared plus x plus 1 has a horizontal asymptote for x to infinity. This means that for very large x, the graph approaches a horizontal line very closely. In this case, the line y equals 2. Notice that the graph also approaches this line for very large negative x. So it is also an asymptote for x to minus infinity. A rational function has a horizontal asymptote if the degree of the numerator is at most the degree of the denominator. You can find the location of a horizontal asymptote for a rational function by dividing both numerator and denominator by the largest power of x in the denominator. For very large x, the terms 1 over x squared, etc. tend to 0. So both numerator and denominator become a constant. In this way, you can determine the height of a horizontal asymptote. A rational function can also have vertical asymptotes. Consider f of x equals 1 over x minus 2. For x equal to 2, the denominator becomes 0 and the function is not defined. For x slightly more than 2, this becomes 1 over a small positive number, which is very big. For x slightly less than 2, it is 1 over a small negative number, which is large negative. Therefore, the graph has a vertical asymptote at x equals 2. a rational function can only have vertical asymptotes at zeros of the denominator. Now, consider g of x equals x minus 1 over x minus 1 times x minus 2. This can be simplified to f of x. However, g is not defined at x equals 1, whereas f is. Apart from this difference in domain, the functions are equal. In the graph, we denote the fact that 1 is not in the domain by adding an open circle at x equals 1. Notice that g has no vertical asymptote at x equals 1, even though this is a 0 of the denominator. This is because the numerator also vanishes at x equals 1. Finally, consider the graph of x plus 2 plus 1 over x plus 1. For very large values of x, the 1 over x plus 1 becomes very small, and the graph of the function thus approaches the line y equals x plus 2. Similarly, for very large negative x, the line y equals x plus 2 is called an oblique asymptote. A rational function can only intersect the x-axis if the numerator is 0. But beware! As you saw in a previous example, if numerator and denominator have the same 0, then this point is not in the domain of our function. Thus, it is not a 0 of the rational function. The zeros of a rational function are precisely those zeros of the numerator for which the denominator is non-zero. The locations of the zeros can heavily influence what the graph of a rational function looks like. For example, compare x minus 2 over x minus 1 times x minus 3 to x over x minus 1 times x minus 3. Both graphs have vertical asymptotes at x equals 1 and x equals 3, the zeros of the denominator. Since the degree of the numerator is less than the degree of the denominator, both graphs have a horizontal asymptote at y equals 0. But the first function has a 0 in between the two asymptotes at x equals 2, and the second function has a 0 to the left of either asymptote at x equals 0. Therefore, the two graphs are quite dissimilar. To summarize, rational functions are the quotient of two polynomials. A rational function can only be defined for the x values for which the denominator is unequal to 0. You add rational functions by making the denominators equal. The graph of a rational function often has asymptotes. Horizontal asymptotes can be found by dividing both numerator and denominator by the highest power of x occurring in the denominator. Vertical asymptotes can be found by looking at the zeros of the denominator. The zeros of the rational function are found at the zeros of the numerator. Good luck with the exercises.
Hi there! In this video we will consider so-called power functions. A power function is a function of the form x to the power a, with a constant, called the exponent. They occur at many places in and outside mathematics. A few examples. The area of a disk of radius r is given by pi times r to the power 2. If you know the volume V of a cube, the size of an edge is given by V to the power 1/3. A last example. If a satellite has distance r to the center of the Earth, then the gravitational force on the satellite is proportional to r to the power -2. The properties strongly depend on whether the exponent is positive or negative and whether it is integer or not. In this video, we focus on integer exponents. Let's first restrict to the case that a is an integer, larger than or equal to 0. In this case, a power function is a special case of a polynomial of degree a. It is also called a monomial and can be seen as a repeated product. For a is 0, it is just the constant 1. For a equals 1, we have x. For a equals 2, we have x squared. For a equals 3, we have x cubed, etc. For power functions with positive integer exponents, we easily check the following rules of calculation. X to the power a times x to the power b is a product of a plus b x's, and is therefore equal to x to the power a plus b. X to the power a to the power b is a product involving b factors of x to the power a, and is therefore equal to x to the power a times b. And x times y to the power a is a product of a factors x times y. Reordering the terms leads to x to the power a times y to the power a. To be able to deal with power functions, it is important that you know these rules. Let's look at some graphs. X to the power 0 is just the constant 1, and x to the power 1 is just x. So their graphs are straight lines. The graph of x squared is a parabola. The graph of x cubed looks like this. And here we see the graph of x to the power 4 and x to the power 5. If we plot the graphs of even powers of x into one single picture, we see the similarity. And if we do the same for the odd powers of x, we also see quite similar graphs. For even powers, the graphs are line symmetric in the vertical axis. These functions are called even, which means that f of minus x equals f of x for all x. For odd powers, you can first reflect the graph in the vertical axis and then in the horizontal axis, and you will end up with the same graph. Another way to look at it is as follows. If you rotate it half a turn around the origin, we say the graph is point symmetric in the origin. In formulas, this means that f of minus x equals minus f of x for all x. Such functions are called odd. Now, let's look at x to the power a with a negative integer. We can use the rules of calculation to define these. For example, what should x to the power minus 3 be? Well, according to the rules of calculation, x to the power 3 times x to the power minus 3 should be equal to x to the power 0, which equals 1. This implies that x to the power minus 3 should be 1 over x to the power 3. In this way, we can define x to the power a with a negative integer as follows. For a equal to minus 1, we have 1 over x. For a equals minus 2, we have 1 over x squared. For a equal to minus 3, we have 1 over x cubed, etc. For these negative values of a, the graphs are quite different. The graph of x to the power minus 1 is called a hyperbola. For a equals minus 2, the graphs look like this. This is the graph of x to the power minus 3. For a equal to minus 4, it looks like this. All these graphs have a horizontal and a vertical asymptote. In general, the following holds. If a is negative, the graph of x to the power a has a vertical asymptote at x equal to 0, and a horizontal asymptote at y equal to 0. We have the same symmetries as for positive powers. For even powers, the functions are even, and therefore the graphs are symmetric in the vertical axis. For odd powers, the functions are odd, so the graphs are point symmetric in the origin. The rules of calculation completely extend to the negative powers as well, as long as x is non-zero. In fact, we can add a rule. X to the power a divided by x to the power b equals x to the power a minus b. This is just a consequence of the first rule and the definition of negative powers. Well, so far we looked only at integer exponents. What about non-integer powers? More about that in the next video. In the previous video, we only considered power functions with integer exponents. Now we will turn to the case of non-integer exponents. How to define power functions in that case? For negative x values, it is only possible in exceptional situations. So first, we restrict to positive values of x. We can use the rules of calculation to define the power function when a is a fraction. For example, what should x to the power 1 over 4 be? Well, according to the rules of calculation, we should have that x to the power 1 over 4 to the power 4 is equal to x to the power 1, which equals x. We define x to the power 1 over 4 to be the positive number which has x as fourth power. That is, x to the power 1 over 4 is the fourth root of x. In this way, we define x to the power 1 over n, with n a positive integer, as the nth root of x. Let us look at the graphs of these power functions. For even values of n, the graphs look quite similar. These functions are only defined for non-negative values of x. For odd values of n, the graphs look quite similar too, and are defined for all real values of x. These graphs are also point symmetric in the origin. Using the power functions that we have defined so far and the rules of calculation, we can define more general power functions. For example, x to the power 2 over 3 is equal to x squared to the power 1 over 3, which is the same as the cube root of x squared. On the other hand, it's also equal to the square of the cube root of x. And x to the power minus 5 over 2 is equal to 1 over x to the power 5 to the power 1/2, which is 1 over the square root of x to the power 5. On the other hand, it is equal to 1 over the 5th power of the square root of x. In this way, we have defined x to the power p over q, with p and q positive integers, as the qth root of x to the power p, or the qth root of x to the power p. And x to the power minus p over q as 1 over the qth root of x to the power p, or as 1 over the qth root of x to the power p. Not every number is a quotient though. For example, square root of 2 cannot be written as a fraction of two integers. How do you define power functions for such exponents? Well, this is a bit tricky, and we will return to this in the next week when dealing with exponential functions. However, I will show you the properties of power functions for general exponents. The first question is, for what x values are they defined? Well, in general, we have that if a is larger than or equal to 0, then the function is defined for x larger than or equal to 0. If a is negative, then we have to exclude x equal to 0. If a happens to be integer and non-negative, then x to the power a is defined for all x. If a is negative, then again we exclude x equal to 0. There are some non-integer exponents for which this holds as well. To be precise, if a equals p divided by q, where p and q are integers and q is odd. I'll be honest, you will probably rarely have to deal with such exponents for negative x. As for the graphs, if a is positive, they are increasing for positive x. If a is negative, the graph decreases for positive x. Furthermore, in that case, the graphs have asymptotes along the horizontal and vertical axis. If the power functions happen to be defined for negative x as well, the graph has symmetries. It's either line symmetric in the y-axis or point symmetric in the origin. Finally, let's have a look at the rules of calculation that we encountered before. as long as x and y are positive, these rules are true for any choice of a and b. But for other values of x and y, it depends. Problems may occur for negative or non-integer exponents. More about that in the exercises. That was a lot of information. To get a feeling for all the different properties of power functions, make sure you have a look at the exercises. Good luck! Did you find the error? The funny thing is that the whole derivation is correct if we would restrict to x larger than or equal to 0. Indeed, in that case, the square root of x squared is equal to x. But this is not true for negative x. So, what went wrong? Well, if x is negative, the rules of calculations of power functions lead to problems, or are simply not true in general. Okay, I'll admit, as long as the exponents are positive integers, there's no problem. But especially for fractional exponents, you must be cautious. You can see this in our derivation. In this step, we split the product, and here a problem arises if x is negative. The expressions after this step is not defined for negative x. After the next step, the expressions again are defined for the negative x. But we made an illegal move in the middle, and this actually caused the problems. In general, if you want to be on the safe side, only apply the rules of calculations for the power functions if the arguments are positive or the exponents are integer. Welcome to the first Catch the Error video. In the Catch the Error videos, we will present a derivation that contains an error. Your task is to identify that error. You can discuss your ideas on the forum below this video. I will rewrite the following expression, the square root of x squared, using the rules of calculation for power functions. First note that x squared equals x times x, so I can write this expression as the square root of x times x. Now remember that square root is a power function with exponent a half, so let me rewrite this as x times x to the power a half. By the rules of calculation for power functions, we can rewrite this as x to the power a half times x to the power a half. By another rule of calculation, we can simplify this to x to the power a half plus a half, which is just equal to x. We conclude that the square root of x squared is x, but this is wrong. Why? Well, let's take x is minus 1. If we plug it into the left-hand side, which is equal to the square root of x squared, we get the square root of minus 1 squared, which is equal to the square root of 1, which is equal to 1. But if we plug it into the right-hand side, which is just x, we get minus 1. So we get that 1 equals minus 1, and that is not true. Do you know what the mistake is here?
Hi there. We've already seen quite a few examples of functions, and we will see many more. In this video, I would like to stop for a moment and ask the following questions. Given a function, what numbers can you put into it, and what numbers do you want to put into it? Let me explain what I mean. First of all, we have defined functions in terms of formulas. For example, fx equals 1 divided by x minus 3. But some formulas do not make sense for all values of x. Here, fx is not defined for x equal to 3. To understand the behavior of a function, you have to know for which input values it is defined. As for the second question, consider the following example. If a cube has edges of side x, its volume is equal to x cubed. This is the volume function of the cube. In principle, this function is defined for all values of x, but given the context, it makes no sense to put in negative numbers. So in this case, it's natural to restrict the input values to numbers larger than or equal to 0. Given a function, it's often natural or even necessary to restrict the set of input values. That is, we have to choose the domain of the function. Remember the setup. A function is defined by 3 pieces of data: the domain, the set of possible inputs, the codomain, a set in which the outputs end up, and a rule that associates to every element in the domain an element in the codomain. In previous videos, we mainly focused on the rule that tells you how to get from the input to the output. Now, I'd like to look more closely at the domain. As an example, consider the function fx equal to 2 plus square root of x minus 3. I did not specify the domain. What options do we have? Well, the only restriction is that we cannot take square roots of negative numbers. So in this case, the function is defined precisely for x minus 3 larger than or equal to 0. That is, x must be larger than or equal to 3. The set of such x is the largest possible domain we can choose, called the maximal domain. In this case, it is the interval 3 to infinity, including 3. Often we will not mention the domain of a function explicitly and silently take it to be the maximal domain. However, sometimes the context makes restrictions natural. For example, think again of the volume function of a cube. The maximal domain is a set of all real numbers, which we denote by R. But given the context, it's natural to restrict to the set of numbers larger than or equal to 0, since only then the volume makes sense. Okay, enough about the input side of functions. What about the output side? There are 2 related concepts here: codomain and range. Remember, the codomain is a set that contains the possible outputs of the function. And let me stress here, I say it contains. It does not have to be exactly equal to the set of possible outputs. You can take it larger if you like. Since every function that we consider produces real numbers, we can just take the set of all real numbers as a codomain. From now on, we will always make this choice. Much more interesting is the range of a function. This is precisely the set of all possible values that the function can attain. Note, it can be smaller than the full codomain. Let's look again at the example function, fx equal to 2 plus square root of x minus 3. In this case, the range is the interval from 2 to infinity. You can clearly see this from the graph. It starts at height equal to 2 and then keeps increasing. In general, the range is the set of all y values for which fx equal to y has a solution. And indeed, you can show that for this function, the equation has a solution precisely if y is larger than or equal to 2. I invite you to try that yourself. The range of a function may depend on the chosen domain, and to illustrate this, let me return to the cube once more. The maximal domain is the set of all real numbers. In that case, the range is a set of all real numbers as well. But for the natural domain, we left out the negative values of x. Choosing this domain, the range is also the set of all numbers larger than or equal to 0. And this makes sense, since volumes cannot be negative. To summarize, we considered domain, codomain, and range. If we do not specify the domain of a function, we just take it to be maximal. Sometimes the context makes it more natural to restrict the domain. We will always take the codomain equal to R. And finally, remember that the range depends on the chosen domain. In general, determining the maximal domain and the range of a given function involves solving equations and inequalities. This can be quite difficult, and we will return to these matters in week 3 and 4 of the course. In the following exercises, you can practice with domains and ranges of standard functions and simple combinations. Good luck!
Hi there! Suppose you make a film of a moving basketball. If the film has a low frame rate, which means that there are not many pictures taken in 1 second, the motion of the ball looks a bit jerky. If you want to see a more fluid motion, you need pictures of the ball taken at shorter time intervals, that is, at a higher frame rate. The shorter the time intervals between the pictures, the more fluid the motion looks. This is because the distance traveled by the ball is a continuous function of time. What does this mean? Well, here is the graph of a function f describing the distance traveled by the ball. You can see that f of 3 equals 2. If we now take a point x on the horizontal axis, which is close to 3, you see that the value of f at x stays close to 2. We say that the function f is continuous at the point 3. The function that you see here is actually continuous at any point p, because if we take a point x which is close to p, then f of x will be close to f of p. In other words, a small change on the horizontal axis will only give a small change on the vertical axis. A function that is continuous at any point p in the domain is called a continuous function. So the function f that you see here is continuous. Not every function is continuous. Suppose you make a film of the balance on your bank account. At a certain point, you see the balance change from, say, 50 to 150. No matter how high the frame rate of your film is, the balance always jumps. The change will never look fluid. If you look at the graph of this function, which is the amount of money on your bank account, you can see that a small change on the horizontal axis from t is 1 to the left will always result in a change on the vertical axis of 100, that is, a large change. This is an example of a discontinuous function. This function, the balance on your bank account, can be described with a piecewise defined function. That is, the function itself is given on different intervals by different formulas. In this case, the function can be given by f of t equals 50 for t less than 1 and f of t equals 150 for t greater or equal to 1. The open dot in the graph indicates that the value of f in 1 is not 50, and the closed dot indicates that it is 150. Another example of a piecewise defined function is the absolute value function, which is defined to be minus x for negative x, and the value is x for non-negative x. Note that the absolute value function is continuous, but piecewise defined functions are often discontinuous, as is the function on the left here. You see that the graph of this discontinuous function makes a jump, so the function skips values in between. For a continuous function, this never happens. To be more precise, a continuous function has the intermediate value property. This says that if f is a continuous function on a closed interval ab, then it attains all values between f of a and f of b. For the graph of f on this interval, it means that you can draw the graph without having to take your pen off the paper. The intermediate value property guarantees, for instance, that the equation x to the power 5 minus x squared plus 1 equals 0 has at least one solution on the interval minus 1, 0, even though we cannot calculate it exactly. This is because the function x to the power 5 minus x squared plus 1 is continuous, and it attains positive and negative values on the interval minus 1, 0, so it must also be 0 at some point. You can clearly see this from the graph. If f is not continuous, the intermediate value property might not hold. For example, if the balance of your bank account goes from 50 to 150, it has not attained any of the values in between. Most of the functions that you've seen so far are continuous functions. For example, polynomials, but also rational functions and power functions are continuous on every point of their domain. For instance, the function 1 over x is continuous on its domain, which consists of all real numbers except 0. Sometimes this causes confusion because the graph makes a jump at x equals 0, but this is not a point in the domain. If we make a new function out of two continuous functions by adding, multiplying or dividing them, we get again a continuous function. For example, the square root of x divided by x minus 1 is continuous on its domain, that is, on numbers larger than or equal to 0, except 1, because it is the quotient of two continuous functions. Be careful though with piecewise defined functions. For example, the function which is equal to x for x less than 0 and equal to 1 for x greater or equal to 0 is made of continuous functions, namely the functions x and the constant function 1. But f itself is not continuous because there is a jump at x equals 0. Continuous functions have nice properties, such as the intermediate value property. as we have seen, this plays a role in solving equations. Realize, however, that not every function is continuous, so it is important to be able to see whether a function is continuous or not. You can practice this in the exercises.
Hi, we're almost at the end of the first week, and we have seen a lot of topics. To get you ready for the homework, I will summarize the most important content of the past week for you. This week was all about functions and their properties. We started with a general definition. A function can be seen as a machine that takes its input from a certain set, called the domain, and then produces an output that ends up in a set called the codomain. Remember that we only considered functions that send real numbers to real numbers. So the codomain can always be chosen to be R. However, the domain does not have to be all real numbers. Given the context, it may be more natural to restrict the domain, and sometimes the defining formulas are simply not defined for certain input values. Once the domain is chosen, you can look at the range, the set of values that the function can attain. This set can be smaller than the full codomain. We've seen 4 ways to describe a function: by means of a formula, using a table, using a graph, and in words. It's important that you can switch between these types of description. We then considered specific types of functions, starting with polynomial functions. Polynomial functions can be constructed from a variable and a set of numbers using only addition and multiplication. Any polynomial can be put into its standard form, in which no brackets occur anymore, every power of x occurs once, and the terms are ordered from high power to low. The highest occurring power in standard form is called the degree. As we have seen, the degree determines the behavior of the polynomial function as x grows large. Also, the higher the degree, the more complicated the function and its graph may behave. It's important to understand the behavior of polynomial functions of low degree. Polynomial functions of degree 0 are of the form p of x equals a. They're constant functions. Polynomials of degree 1 have standard form a times x plus b. The graph is a straight line with slope a and y-intercept b. Polynomial functions of degree 2, also called quadratic functions, are of the form a times x squared plus bx plus c. The graph of any such function is a parabola. It's often useful, when possible, to rewrite a quadratic function in factorized form: a times x minus p times x minus q. P and q are the x values where the graph intersects the horizontal axis. Another useful form is the complete square form: a times x minus r squared plus s. R and s are precisely the coordinates of the vertex of the parabola. The second class of functions that we considered are rational functions. These are precisely the functions that can be constructed from a variable and a set of numbers using addition, multiplication, and division. Any rational function can be written as a quotient of 2 polynomials. In the exercises, you saw how to do this. The graph of a rational function may have asymptotes, straight lines that are approached by the graph. Vertical asymptotes, where the function grows to plus or minus infinity, can occur at x values for which the denominator vanishes. Be careful though. If the numerator vanishes as well, an asymptote may be absent. Horizontal asymptotes occur precisely if the function tends to a constant for x much larger or much smaller than 0. The common technique to find such asymptotes is to divide numerator and denominator by the highest power of x occurring in the denominator. Then you see clearly what happens as x grows large. The final class of functions that we considered are the functions of the form x to the power a, the so-called power functions. The domain depends on a. All power functions are defined for x bigger than 0. However, if x equals 0, x to the power a is only defined for positive a. For negative x, it's more complicated. There's no problem if a is an integer. For non-integer a, it's usually not defined. But there are exceptions, like x to the power 1/3. For the graphs of power functions, we have the following in general. If a is bigger than 0, it is increasing for positive x. The larger the exponent, the faster it grows for large x. For a smaller than 0, the graph is decreasing. In this case, we have the smaller a, the closer to 0 from large x. For integer exponents, the graphs have symmetry properties. They are line symmetric in the y-axis if a is even, and point symmetric in the origin if a is odd. Finally, power functions obey certain rules of calculation that you should know. X to the power a times x to the power b equals x to the power a plus b. X to the power a divided by x to the power b equals x to the power a minus b. X to the power a to the power b is equal to x to the power a times b. And finally, x times y to the power a equals x to the power a times y to the power a. If x and y are positive, these rules hold for all a and b. Be careful for other values of x and y. Then, problems may arise for negative and non-integer exponents. All the functions that we treated share a property. They are continuous on their maximal domain. Roughly, a function f is called continuous if the following holds. If you can change x by a small amount within the domain of f, fx will also change by a small amount. In particular, the function values cannot jump. If f and x are continuous functions, then so is their sum, product and quotients, whenever those are defined. If a continuous function is defined on an interval from a to b, including a and b, then we will attain all values between fa and fb. This is called the intermediate value property. Intuitively, it means that you can draw the graph on the interval without lifting your pen. You should be aware that not all functions are continuous. For example, functions that have graphs with jumps. Such functions have to be defined piecewise using different formulas on different intervals. Conversely, given such a piecewise defined function, you should be able to tell whether it has jumps or not. These were the main topics of this week. Good luck with your homework.
Do you know how your calculator calculates square roots? In this video, I will show you the essential idea. Welcome to this, the first university preview. Mathematics does not end at high school, and each week we will try to give you a view of some cool things you might learn about at university. This week, I will give a short introduction to Taylor polynomials. While some other methods are used as well, many calculators use Taylor polynomials when calculating a square root, and also for other functions, such as the sine and exponential function. Let us consider the graph of the function square root of 1 plus x, and look at the point x equals 0.6. That is, we want to calculate the square root of 1.6. A first approximation might be to say that 0.6 is close to 0, and thus the value of our function at x equals 0.6 is approximately equal to the value at x equals 0, which is 1. In essence, we are approximating the graph of the function with a horizontal line at height 1. Can we find a better approximation of the graph near x equals 0? Well, there is of course the tangent line. The tangent line is a straight line which is tangent to the graph at x equals 0. If we draw this line, you see that it is a better approximation to the graph than the horizontal line we drew before. In school, you probably learned how to calculate the equation for the tangent line, and we will review this in week 5. In this case, the tangent line is given by the equation y equals 1 plus x over 2. Plugging x equals 0.6 into this equation, we obtain that square root of 1.6 is approximately 1.3, which is a better approximation of the square root of 1.6 than 1 is. To obtain an even better approximation of our square root, we first realize that 1 plus x over 2 is a polynomial of degree 1. Thus, we can try to approximate our function not with a polynomial of degree 1, but with a polynomial of higher degree instead. Let's start with 2. It turns out there is one polynomial of degree 2 which best approximates square root of 1 plus x near 0. This is called the Taylor polynomial of degree 2. The formula for the tangent line is calculated using the derivative. In fact, the function 1 plus x over 2 giving the tangent has the same value and derivative as the function square root 1 plus x at x equals 0. The degree 2 Taylor polynomial can be calculated by also insisting that the second derivative of f equals the second derivative of the approximating polynomial. The result is 1 plus x over 2 minus x squared over 8. As you can see, this tracks the graph of square root 1 plus x pretty well. A better approximation for square root 1.6 is thus 1.255. But we are not yet satisfied with our approximation. We want 10 digits to fill up the screen of our calculator. How can we make an even better approximation? Well, we could try approximating our function with a degree-free polynomial. The best approximation of f with a degree-free polynomial is the Taylor polynomial of degree 3. And it turns out to be the one on the slide. The approximation of square root 1.6 becomes 1.2685. We made an adjustment of just 0.01, so we might be confident in our first two digits, 1.26. Indeed, in this case the approximation always improves if you use a higher degree polynomial. To get to 10 digits, it turns out we need to calculate the degree 32 Taylor polynomial. This polynomial contains 33 terms, and it might still sound a lot of work to add up 33 numbers. But for a calculator, this is of course no work at all. In particular, we have reduced calculating a square root to simpler operations as multiplication and addition. Most functions you will encounter can be approximated by Taylor polynomials. The advantage of using Taylor polynomials instead of the original function is that polynomials are some of the easiest functions around. Thus, however complicated a problem gets, you can always make it simpler by turning every function in sight into its Taylor polynomial. One question you should ask yourselves whenever you approximated anything is how big the error is. An approximation is only useful if the error is small. So you can ask yourself questions like, how does the error change if I change the degree of the polynomial? How does the error change if I calculate square root of 1.2 instead? Do I also get good approximations for different functions? And of course, the fundamental questions, how do I even calculate these Taylor polynomials? At university, you can explore these questions and others.
Hi! In this video, we will introduce the trigonometric functions. Trigonometric functions arise in periodic phenomena such as acoustic waves and water waves, and also in circular movements such as a big wheel or Ferris wheel. Here we see the London Eye, also called the Millennium Wheel, since it was built at the occasion of the Millennium Change at the year 2000. At that time, it was the world's largest Ferris wheel. Its height is 135 meters, it contains 32 closed cabins, and it takes 30 minutes for one tour. The height of a cabin of the London Eye as a function of time can be described by means of trigonometric functions. Let us assume that at time t is 0, a cabin is in its lowest position so that people are able to enter. Furthermore, we assume that the big wheel turns at a constant speed and that it takes 30 minutes for a complete tour. After 7.5 minutes, the cabin has reached half of its maximum height, and after 50 minutes, it is at its highest position. Then the cabin is going down, and after 22.5 minutes, it is back at half of its maximum height. After 30 minutes, it is back down at its lowest position. From there, the movement is repeated and we end up with a periodic function. The trigonometric functions are usually defined as the ratio of two sides in a rectangular triangle. For the acute angle theta, we have the sine of theta is the length of the opposite side divided by the length of the hypotenuse. The cosine of theta is the length of the adjacent side divided by the length of the hypotenuse. And the tangent is the length of the opposite side divided by the length of the adjacent side, which equals the sine of theta divided by the cosine of theta. In mathematics, angles are usually measured in radians instead of degrees. The angle of a complete revolution contains 360 degrees, which is equal to 2 pi radians. The number pi is a quite complicated number, which is close to 3.14. So we have pi radians equals 180 degrees. This implies that 1 radian equals 180 over pi degrees, and that 1 degree equals pi over 180 radians. If we consider a sector with angle theta in a circle with radius r, then the length of the arc S equals theta divided by 2 pi times the circumference 2 pi r of the complete circle, which is the radius r multiplied by the angle theta. If we take a circle with radius 1, then the arc S is equal to the angle theta measured in radians. Since the trigonometric functions only depend on the ratio of two sides of a rectangular triangle, we might draw this triangle inside a circle with radius 1, being the hypotenuse of the triangle. This circle is called the unit circle. Then we have for an acute angle theta that the value of the sine can be found at the vertical axis and the value of the cosine at the horizontal axis. Both are positive for acute angles. The value of the tangent is the indicated height at the vertical line tangent to the circle, which explains its name. In this way, we can collect the values of the trigonometric functions for special values of the angle theta between 0 and pi over 2. We consider the angles 0, pi over 6, pi over 4, pi over 3 and pi over 2. For the sine, we obtain these values using the vertical axis, and for the cosine, we obtain these values using the horizontal axis. Then the value of the tangent is obtained by the ratio of the sine and the cosine. Of course, this does not exist for theta is pi over 2, since then the cosine is equal to 0. Now the unit circle can be used to define both the sine and the cosine for other values of the angle theta as well. For instance, consider theta is equal to 2 pi over 3. This angle is indicated in the picture, and we have to determine the indicated values at the horizontal and the vertical axis. Note that the value of the cosine at the horizontal axis is negative, and that the value of the sine at the vertical axis is positive. In this way, we can find the values of the sine and the cosine for all special values of the angle theta in the unit circle. Let us look at an example. If we want to find the value of the cosine of 5 pi over 6, we make a turn with an angle of 5 pi over 6 in the positive direction, which is counterclockwise, till we have reached 5 pi over 6 on the unit circle. Now we look at the horizontal axis and obtain the value minus 1/2 times the square root of 3. For the value of the sine of 5 pi over 6, we look at the vertical axis and obtain the value plus 1/2. Now the value of the tangent is the quotient of the sine and the cosine, which is equal to plus 1/2 divided by minus 1/2 times the square root of 3, which simplifies to minus 1/3 times the square root of 3. Another example. If we want to find the value of the cosine of minus 2 pi over 3, we make a turn with an angle of 2 pi over 3 in the negative direction, which is clockwise, till we have reached minus 2 pi over 3 on the unit circle. Now we look at the horizontal axis and obtain the value minus 1/2. For the value of the sine of minus 2 pi over 3, we look at the vertical axis and obtain the value minus 1/2 times the square root of 3. Now the value of the tangent is the quotient of the sine and the cosine, which is equal to minus 1/2 times the square root of 3 divided by minus 1/2, which simplifies to the square root of 3. Finally, we look at the graphs of the trigonometric functions. Both the cosine and the sine are defined for all real values of the angle, which is the argument of the function. The graph of the cosine looks like this, and the graph of the sine like this. Since the tangent is the ratio of the sine and the cosine, it is well defined for all values of x for which the cosine is not equal to 0. At the zeros of the cosine, the graph has vertical asymptotes. In the next video, we will cover the main properties of these trigonometric functions, as well as their rules of calculation. Good luck with the exercises. Welcome back. In the previous video, we have introduced the trigonometric functions. From the definitions, we can derive several important properties, which lead to rules of calculation that we can use to solve equations involving these trigonometric functions. For instance, look at the rectangular triangle with hypotenuse equal to 1. Then the Pythagorean theorem leads to cosine squared plus sine squared equals 1. In fact, this holds for all real theta. From the unit circle, it is clear that both the cosine and the sine are periodic functions. In fact, if we make a complete turn counterclockwise, which is the positive direction, we run through the same values of the angle theta again. This implies that the cosine of theta plus 2 pi equals the cosine of theta, and that the sine of theta plus 2 pi equals the sine of theta. Moreover, if we make a complete turn clockwise, which is the negative direction, we also run through the same values of the angle theta again. This implies that the cosine of theta minus 2 pi equals the cosine of theta, and that the sine of theta minus 2 pi equals the sine of theta. This implies that the unit circle can be used to find the values of both the cosine and the sine for all values of the angle theta. Both functions are periodic with period 2 pi. The periodicity of the cosine and the sine also becomes clear from their graphs. A shift of 2 pi in both the positive and negative direction leads to the same values for both the cosine and the sine. The graph of the tangent shows that this function is periodic too. However, it has period pi instead of 2 pi. Back to the rectangular triangle. Consider the indicated angle in the top corner, which equals pi over 2 minus theta. For this angle, the opposite side and the adjacent side of the rectangle are reversed, which shows that the cosine of pi over 2 minus theta equals the sine of theta, and that the sine of pi over 2 minus theta equals the cosine of theta. The periodicity of both functions shows that these formulas hold for all values of theta. Back to the unit circle and consider the angle theta. Then, reflection in the horizontal axis show that the cosine is an even function, which means that the cosine of minus theta equals the cosine of plus theta. And that the sine is an odd function, which means that the sine of minus theta equals minus the sine of theta. The graph of the cosine is line symmetric in the vertical axis, which shows that the cosine is even, and the graph of the sine is point symmetric in the origin, which shows that the sine is odd. the graph of the cosine also shows that the cosine of pi minus x equals minus the cosine of x, and the graph of the sine also shows that the sine of pi minus x equals the sine of x. Finally, we will derive the so-called addition formula for both the sine and the cosine. That is the formula for the sum of two angles. We start with a rectangular triangle with hypotenuse equal to 1. Then the opposite side of the angle alpha equals the sine of alpha, while the adjacent side equals the cosine of alpha. Now we add an angle beta and create two extra rectangular triangles. Consider the lower one with hypotenuse equal to the cosine of alpha instead of 1. Then we easily obtain the length of both the opposite and the adjacent side of the angle beta involving this vector cosine of alpha. Then we consider the upper rectangular triangle with hypotenuse equal to the sine of alpha instead of 1. Similarly, we obtain the length of both the opposite and the adjacent side of the angle beta involving this vector sine of alpha. So we have this. Now we create an extra rectangular triangle with one of the angles equal to the sum of alpha and beta. Note that the hypotenuse of this triangle is equal to 1. This implies that the sine of alpha plus beta is equal to the length of the red sides. This is the addition formula for the sine. For the cosine of alpha plus beta, we must have the green side, which is the difference between the blue side below and the orange side above. This leads to the addition formula for the cosine. If we take both alpha and beta equal to x, these formulas lead to the double angle formulas for the sine and for the cosine. This proof only holds for acute angles alpha plus beta. However, both formulas hold for all values of alpha and beta. All formulas derived in this video can be useful in solving equations involving trigonometric functions. Good luck with the exercises.
Hi, and welcome to another Catch the Error exercise. I'll make a calculation and you have to be on the lookout for the mistake. Suppose I know that the sine of 127 equals about 0.8, but I would like to know the cosine instead. Of course, I could use my calculator to directly calculate cosine 127, but unfortunately I left it at home. But recall, there is an equation relating cosine and sine at the same angle. So we can use this equation instead. This relation is sine of x squared plus cosine of x squared equals 1, which is just the Pythagoras theorem. So applying it here, we find that the cosine of 127 squared equals 1 minus the sine of 127 squared. So we fill this in and we find that the cosine of 127 squared is equal to 0.36. So we take the square root, and now we know that the cosine of 127 is about 0.6. I was very happy with this result, but then later on I checked it on my calculator and this answer turned out to be wrong. Can you determine the correct answer and see where I went wrong? So, did you find the error? You could have realized the answer was incorrect as soon as you saw that it was positive. The cosine of 127 is negative, which can be seen directly in a unit circle as the x-coordinate of this point is negative. We can also look at the graph of the cosine and notice that it's below the y-axis for 127 degrees. Indeed, any cosine for an angle between 90 and 270 degrees is negative. This shows that my answer is wrong, but not where I made the mistake. let's go back to the calculation. I derived the value of cosine of 127 squared using cosine of x squared plus sine of x squared equals 1, and this is fine. But then I conclude that cosine of 127 must be the square root of 0.36. But of course there's another number with the same square, 0.36, namely minus the square root. So cosine of 127 equals minus the square root of 0.36, and this is minus 0.6. So this must be the correct value of cosine of 127. Indeed, knowing that cosine of 127 must be negative and that its square must be 0.36 implies that it equals minus 0.6. Going back to the unit circle, you can see that there are 2 points in the unit circle where the sign equals 0.8. One with a positive cosine and one with a negative cosine. And that was where we made the error.
Would you like to know how to reduce complicated expressions into smaller, simpler pieces? In this video, you will learn about the concept of composition, which will help you to break up those complicated expressions in manageable pieces. In order to have a large library of functions to use in modeling real-world phenomena, we need more than just the basic functions we have been telling you about. You can combine polynomials and signs by, for example, adding them or multiplying them. One of the more complicated ways to combine two functions is to compose them. The most tricky rule of differentiation, the chain rule, deals with composed functions, as you will see in week 5. If you consider a function to be a machine with inputs on the left and outputs on the right, a composed function is akin to an assembly line. We take two functions, let us say sine and square, and put them in a line. Moving the input x first through the sine, the intermediate outcome is sine of x. Then, moving this through the square function, we end up with sine of x squared. Together, they form a new function, the composition of x squared, the rightmost function, with sine x, the leftmost function. If we had put the boxes in opposite order, we would have obtained x goes to x squared goes to sine of x squared, which is the composition of sine x with x squared. Notice that these two expressions are not equal. If we plug in x equals 1, we obtain either sine of 1 squared is approximately 0.71, or sine of 1 is approximately 0.84. The order of operations matter. Of course, this is true of a real assembly line as well. A cookie manufacturing line first mixes the ingredients and then puts them in the oven. If it were to first put the ingredients in the oven and then mixes the results, you would not buy the resulting cookies. If you have two functions f and g, their composition is written as f of g of x. So the first function on the assembly line is placed inside the last function. The order in which you apply the functions is important. I can't repeat this often enough. So if you have a composed function, you want to explicitly realize what the inner and outer functions are. I like to designate the inner function by putting a box around it like so. This way I can quickly see the structure of my complicated function. This concept of composition is useful because it allows you to turn complicated problems in multiple simpler ones. As an example, consider the equation x to the 8th plus 2x to the 4th plus 1 equals 4. There is no quadratic formula for degree 8 equations. However, we can see x to the 8th plus 2x to the 4th plus 1 as the composition of f of x equals x squared plus 2x plus 1 with g of x equals x to the 4th. Thus we first solve f of p equals 4, which gives p squared plus 2p plus 1 equals 4. So p equals minus 3 or p equals 1. Hence f of g of x equals 4 whenever g of x equals minus 3 or g of x equals 1. Now we solve the latter two equations, x to the fourth equals minus 3 and x to the fourth equals 1. The first has no solutions and the second has solutions x equals 1 and x equals minus 1. Thus these are the only two solutions to the complicated equation x to the 8th plus 2x to the 4th plus 1 equals 4. Now, try to figure out how you can explicitly see the complicated functions from the exercises as compositions. After the previous video, you might wonder what the graphs of those composed functions look like. Since you can make very many completely different functions, it is impossible to easily describe all of them. In case you compose a function with a linear function, you can see what happens to the graph of the resulting function. In this video, you will learn how. Linear functions, such as f of x equals 2x plus 1, can be viewed as having two characteristics. There's the scaling, times 2, and the translation, plus 1. We will consider these two separately. First, we will consider only the translation. What happens to the graph of a function if you compose it with f of x equals x plus 5? We consider the composition of g of x equals x squared with f. Remember that it mattered in which order we composed. If we look at f of g of x, we obtain the function f of x squared equals x squared plus 5. The graph of this function is equal to the graph of g shifted upwards by 5. And indeed, if we look at x squared plus 5 for arbitrary x, the result is always 5 higher than the value of x squared. So the graph is shifted upwards. Now we consider the composition in the alternative order. G of f of x equals x plus 5 squared. As you can see, the graph is again translated, but now it is shifted 5 to the left. This might seem counterintuitive at first. However, if we consider x plus 5 squared, then the value at x equals minus 5 of x plus 5 squared is equal to the value at x equals 0 of x squared. Thus, the graph of the function is the same, but for x plus 5 squared, the x values must be reduced by 5. That is, the graph must be shifted to the left. Let us now consider scaling. We take f of x equals 2x and g of x equals sine of x. Then f of g of x equals twice sine x. And the graph is equal to the graph of the sine, but stretched by a factor 2 in the vertical direction. Indeed, in general, the value of f of g of x equals 2 times g of x is twice the value of g of x. Thus, the distance of the graph to the x-axis is multiplied by 2. Finally, we have to consider g of f of x equals sine of 2x. In this case, the graph of the sine is shrunk by a factor of 2 to the y-axis. We see that sine of 2x has the same value at x equals 1 as sine of x has at x equals 2. Thus the graph looks identical, but the x values must be shrunk by a factor of 2. We have seen 4 different compositions with separate results for what happens to the graph. G of x plus a gives a vertical shift of the graph a upwards. G of x plus a gives a horizontal shift of the graph a to the left. A times g of x gives a vertical scaling by a factor a from the x-axis, and g of ax gives a horizontal scaling by a factor 1 over a from the y-axis. Now we will apply these rules for scaling and translation to the graph of the sine function. The resulting functions describe all sorts of waves, like sound and light. The formula for these functions has the form f of t equals a times the sine of bt plus c plus d, where we traditionally think of the variable t as time. The values a and b correspond to scaling in the vertical and horizontal directions. A is called the amplitude and gives the difference between the minimum or maximum of the wave and the average value. 2 pi over b is called the period. It is the time between two waves. The values of c and d correspond to translations. C is called the phase of the wave. The phase of a wave does not change what the wave looks like, but tells us at which time it passes through equilibrium. Finally, d determines the average height, the equilibrium position of the wave. Now, you figure out what functions correspond to the graphs in the exercises.
Hi, do you have a savings account at the bank? The interest rate is related to exponential functions. Let's see how. Suppose you have some money, say 200 euros, on a savings account that gives you 3% interest per year. How much money have you got after 10 years? And after 15 years? Or can we give a function that describes how much money you have after X years? Of course, we assume here that you don't make extra deposits or withdrawals. Okay, let's see. After year 1 you get 3% of 200 euros interest. So you have 200 times 1.03 equals 206 euros. After year 2 you get interest over these 206 euros. So 206 times 1.03 equals 212 euros and 18 cents. We can write this as 200 times 1.03 squared. After 3 years you have 200 times 1.03 cubed euros, and so on. So after year x, you have 200 times 1.03 to the power x euros. This is an example of an exponential function. In general, an exponential function has the form a times b to the power x. Here a is some non-zero constant, and b is a positive number called the base of the exponential function. The number x is called the exponent. We will assume that b is not equal to 1, since this would just give you a constant function. The function we found in the example is indeed of this form, 200 times 1.03 to the power x, so a equals 200 and b equals 1.03. In the example, x is a natural number because you only receive the interest on your money once a year. In general, we would like to define b to the power x for any real number x. To do this, we need some properties for exponential functions. We already know calculation rules for power functions. These rules immediately give us rules of calculation for exponential functions with rational exponents. In particular, using the third rule, we know what b to the power x should be if x is equal to p over q, with q larger than 0. It is the qth root of b to the power p. So, what if x is not a rational number? Well, in this case, x can be approximated with rational numbers, and for rational numbers we know what to do. For example, what is 2 to the power the square root of 2? We can approximate the square root of 2 by 1.4, which is the rational number 14 over 10. Then we can approximate 2 to the power square root of 2 by 2 to the power 1.4, which is 2.63, etc. Using more decimals for the square root of 2, we get a better approximation. By taking a limit, we find 2 to the power the square root of 2. Let's have a look at the graph of b to the power x. First, we assume that b is greater than 1. We see that f is an increasing function since, for positive h, b to the power a plus h is a factor b to the power h greater than b to the power a. In the same way, we find that for b smaller than 1, the function b to the power x is a decreasing function. To see how fast an exponential function grows, we compare the graph of 2 to the power x to the graph of x to the power 11. Which function do you think will grow the fastest? Well, look at the graphs. It looks like x to the power 11 grows the fastest. But if we zoom out, we see that 2 to the power x catches up quickly and still grows much faster than x to the power 11. In fact, b to the power x with b greater than 1 grows faster than x to the power n for any number n. A base that is often used for exponential functions is the number e, which is approximately 2.718. Later on in week 5, we will see that the function e to the power x has the special property that it is its own derivative. Now let's summarize. An exponential function is of the form a times b to the power x. We have the rules of calculation for exponential functions, and an exponential function with b greater than 1 grows faster than any polynomial. You will see that exponential functions occur in many different applications. In the exercises, for instance, you will model interest rates and population growth with exponential functions. Welcome back. If I travel to the US and watch the weather forecast there, I see all temperatures in Fahrenheit. To understand them, I need to translate them to Celsius. But if an American comes to Delft in the Netherlands, he has to translate from Celsius to Fahrenheit. This is an example of an inverse function. Converting Fahrenheit to Celsius is a function with domain the square on the left with all possible temperatures in Fahrenheit, and the range is the square on the right with corresponding temperatures in Celsius. An American visiting Delft wants to go from right to left, that is, convert Celsius to Fahrenheit. This is the inverse function. Note that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. What exactly is an inverse function? Suppose f is a function with domain D and range R. So f maps an x in D to a number y in R. The inverse function goes in the opposite direction. That is, it maps each number y in the range R back to its original x in the domain D. In other words, if y equals f of x, then the inverse function is a function f inverse, such that f inverse of y equals x. How can you find the inverse function? For example, take f of x is equal to 3x. The domain and range both consist of all real numbers. We start by setting y equal to 3x. Now the inverse function maps y back to x. That is, f inverse of y is equal to x. If we solve the equation y equals 3x for x, we get x equals 1 over 3 times y. So we see that f inverse of y is equal to 1 over 3 times y. As you know, we can use any letter for the variable of a function. And usually we use the letter x for the variable. And we also do this for inverse functions. So we replace y by x, and we find that the inverse of 3 times x is 1 over 3 times x. You just saw how to find the inverse function. Solve the equation y equals f of x for x, and then interchange x and y. But does this always work? Let us look at the function x squared. To find the inverse function, we must solve the equation y equals x squared for x. This gives two solutions, square root of y and minus the square root of y. And indeed, you can see that, for example, y equals 4 occurs twice in the table. So, if we only know the value of y, we cannot know what the original value of x was. This means that there is no inverse function for x squared. We see that the function f only has an inverse if, for each y in the range of f, the equation y equals f of x has exactly one solution. Functions with this property are called injective. There's an easy way to see if a function is injective. The graph of f must intersect any horizontal line in at most one point. This is called the horizontal line test. If we apply the horizontal line test to the graph of x squared, we see that it intersects a horizontal line at more than one point. So this is not an injective function. However, if we take the positive real numbers as domain of x squared, we see that the graph now intersects horizontal lines at just one point. So now it is injective. In this case, for positive y, the equation y equals x squared has exactly one solution, namely x is equal to the square root of y. Now interchanging x and y, we see that the inverse of x squared with domain the positive real numbers is the square root of x. Let us now look at the graph of an inverse function. Suppose that x, y is a point on the graph of the function f, then y equals f of x. Since x equals f inverse of y, we find by interchanging x and y that y, x is a point on the graph of f inverse. So the graph of f inverse can be obtained from the graph of f by interchanging the x and the y coordinates, which is the same as reflecting the graph of f in the line y equals x. You just saw that the square root of x is the inverse of the function x squared restricted to the positive numbers. So we obtain the graph of the square root of x by reflecting the graph of x squared in the line y equals x. And in the same way, you can obtain the graph of 1 over 3 times x from the graph of 3 times x. Okay, let's summarize. If f is a function with domain D and range R, then f only has an inverse if f is injective, which can be seen using the horizontal line test. If f has an inverse, then f inverse of y equals x precisely when y equals f of x. F inverse has domain R and range D, and the graph of f inverse is obtained from the graph of f by reflecting in the line y equals x. In the next video, we will use inverse functions to define logarithms, but first, try to find another inverse of x squared by using a different domain. Good luck! Hi! In computer science, the smallest unit of information is a bit. It can have two values, 1 or 0, which correspond, for instance, to on or off, or true or false. Here we represent a bit by a box, which can contain a 1 or a 0, so with one box we can make two combinations. By combining boxes, we can make more combinations. For example, there are 4 possible combinations when we use 2 boxes. The more boxes you use, the more combinations you can make. You can ask how many combinations can be made with 3 boxes, or 4, or more general, x boxes. Each box can contain 2 values, so with 3 boxes you can make 2 to the power 3 equals 8 combinations. In general, if we have x boxes, we can make 2 to the power x combinations, so the number of combinations is given by an exponential function. Now suppose you want to make 1,000 combinations. How many boxes do you need? In this case, you need to solve the equation 2 to the power x is equal to 1,000. Just by trying, you find that 2 to the power 9 is smaller than 1,000 and 2 to the power 10 is larger than 1,000. This means that the number x that you are looking for is between 9 and 10, and therefore you need 10 boxes to make at least 1,000 combinations. But what if you want to make at least 10 billion combinations? You really don't want to calculate successive powers of 2 until you pass 10 billion. So we want to solve the equation 2 to the power x is equal to 10 billion. And to do this, we need the inverse of the exponential function 2 to the power x. This inverse is called a logarithm. Let's consider a more general setting. We look at the exponential function with base b larger than 1, so f of x is b to the power x. The function b to the power x is defined for any x, so the domain of f is the whole real line. The range of this function consists of all positive numbers. If we look at the graph of b to the power x, we see that it satisfies the horizontal line test, that is, the graph intersects a horizontal line in at most one point. So from the previous video, we know that f has an inverse function. This inverse is called the logarithm in base b. From what we know from inverse functions, we have the following properties. Log base b is the inverse of b to the power x, so y is equal to log base b of x precisely when b to the power y is equal to x. The domain of log base b is the range of b to the power x and the other way around. For example, log base 2 of 8 is equal to 3 because 2 to the power 3 equals 8. A logarithm can also be negative. For instance, log base 5 of 1 over 5 is equal to minus 1 because 5 to the power minus 1 equals 1 over 5. In general, log base b of b to the power a equals a. Also, note that log base b of 1 equals 0 for any base b, since b to the power 0 is always equal to 1. Although logarithms can be defined for any base b greater than 1, the numbers 10 and e are the most common bases. If the base of the logarithm is the number e, we call it the natural logarithm, and we use the notation ln of x. The logarithm in base 2 is also frequently used, especially in computer science, as you saw in the beginning of this video. If the symbol log is used without a base, the base should be clear from the context. Most often this means the base is equal to 10. Let's go back to the general function log base b of x. Since this is the inverse of the exponential function b to the power x, the graph of log base b of x is the reflection of the graph of b to the power x in the line y equals x. Note that the logarithm tends to minus infinity if x tends to 0. Recall that the exponential function b to the power x grows faster than x to the power c for any positive number c. As a consequence, the inverse of b to the power x grows slower than the inverse of x to the power c, which is x to the power 1 over c. Since d is 1 over c is also positive for any positive number c, we find that log base b of x grows slower than x to the power d for any positive number d. If we compare, for example, the graphs of log base 2x and x to the power 1 over 3, it seems that for x larger than 3, the graph of x to the power 1 over 3 lies below the graph of log base 2 of x. But if we zoom out, we see that x to the power 1 over 3 catches up at some point, and from there it grows much faster. Let's summarize what we know so far about logarithm. First, the logarithm in base b is the inverse of the exponential function b to the power x. And second, a logarithm grows slower than x to the power d for any positive number d. Okay, let's go back to the question from the beginning. How can we solve 2 to the power x is equal to 10 billion? Using a logarithm, we find that x equals log base 2 of 10 billion. But how big is this number? If you want to use a simple calculator to find out, you need rules of calculations for logarithms. We look at these rules in the next video. Hi there! In the previous video we defined logarithms and looked at their graphs. In this video we illustrate the rules of calculation for logarithms with examples. If you are interested in the precise proofs of these rules, you can look in the course notes. The rules of calculation will be very useful when you need to solve equations involving logarithms. And, as promised in the previous video, these rules will also help us to calculate logarithms on a simple calculator. Let's start with this rule. The logarithm of a product is a sum of logarithms. Suppose we can make a combinations of bits, that is, of zeros and ones, by putting them in these m boxes. In the previous video, you have seen that this means that m is equal to the log of a. We have a second set of boxes with which we can make b combinations, so the number of boxes equals n, which is the log of b. If we put all boxes together, we can make a times b combinations, and the number of boxes is n plus m. This means that log of a times b is equal to m plus n, which is equal to log of a plus the log of b, which illustrates the general rule. Let's take the first set of boxes again. We have a combinations and m boxes, so m is equal to the log of a. Now we assume that we have k of these sets. If we put them all together, we have k times m boxes and a to the power k possible combinations of zeros and ones. This gives log of a to the power k is equal to k times m, which is equal to k times the log of a. So we can take the exponent out of the logarithm. In general, this rule is valid for any real number k, not only for natural numbers. Finally, let's look at the change of base formula. Now we look at a slightly different situation. So far, we considered how many combinations we can make with a given number of boxes. That is, if we have n boxes, which can all contain two symbols, namely 0 and 1, how many combinations can we make? Let's say we have 10 symbols now. 0, 1, 2, up to 9. How many combinations can we make in this case? Well, if we have one box, we can of course make 10 combinations. With two boxes, we can make 100 combinations, and in general, with n boxes, we can make 10 to the power n combinations. Let's compare this to the number of combinations with just zeros and ones. Suppose we want to make 100 combinations. In base 10 we need 2 boxes, and in base 2 we need 7 boxes, since 2 to the power 7 is the smallest power of 2 larger than 100. This differs by a factor 2 over 7, which is 0.29. Now what about 1000 combinations? In base 10 we need 3 boxes, since 10 to the power 3 is equal to 1000. And in base 2 we need 10 boxes, since 2 to the power 10 is the smallest power of 2 larger than 1000. This differs by a factor 3 over 10, which is 0.3. Now what about 10,000 combinations or 1,000,000? Here are the numbers for these cases. You can see that the ratio is always about 0.3. What does this tell us about logarithms? Well, the first number on the left is the log in base 2 of the number of combinations that we want. Actually, we rounded it up because the number of combinations that we chose is not the power of 2. The number on the right is the log in base 10 of the number of combinations. So we have the formula log base 10 of a is approximately equal to 0.3 times log base 2 of a, which says that logarithms in base 10 and base 2 differ by a constant factor. We can actually calculate the constant factor. If log base 10 of a equals c times log base 2 of a, then taking a equal to 2 gives c is equal to log base 10 of 2. So the factor 0.3 in our example is actually log base 10 of 2. The change of base formula is very useful for calculating logarithms on a simple calculator. Suppose you want to calculate log base 2 of 500. On your calculator you see a button log for the logarithm in base 10. From the change of base formula it follows that log base 2 of 500 is equal to log 500 divided by log 2. The result on your calculator is then 8.96, etc. If you use the natural logarithm instead, you find the same result. Here you see the rules of calculation for logarithms that you should remember. These will be very useful when you have to solve equations involving logarithms. You should, however, be careful when applying these rules. They only work if all logarithms involved are defined. For example, log base 3 of minus 3 squared is equal to 2, because minus 3 squared is equal to plus 3 squared, and log base 3 of 3 squared equals 2. Applying the third rule then gives 2 is equal to 2 times log base 3 of minus 3. But this is nonsense, because the logarithm of a negative number does not exist. Now, have a look at the exercises.
Welcome to the summary of week 2. This week we considered the trigonometric and exponential functions and logarithms. We first looked at trigonometric functions, that is, the sine, cosine and tangent function. There are two basic ways to define the trigonometric functions: by looking at a right-angled triangle and by looking at the unit circle. In a right-angled triangle with angle theta, the sine of theta is equal to the quotient of the opposite side and the hypotenuse. In the unit circle, it is the y-coordinate of a point rotated counterclockwise over an angle theta from the positive x-axis. The cosine equals the adjacent side over the hypotenuse, or the x-coordinate in the unit circle. The tangent function is equal to the opposite side divided by the adjacent side, and thus satisfies the relation tangent of theta equals sine of theta divided by cosine of theta. Remember that the inputs of these functions are typically angles, and then in calculus we measure angles in radians. The length s of an arc of angle theta equals the radius of a circle times theta. Thus, a full circle is 2 pi radians, because that is the circumference of the unit circle. To convert degrees to radians, you can multiply by a factor of 2 pi divided by 360. You should know the values of the sine and cosine for certain special angles. These are given in the table. Using symmetries, you can extend this table to other special angles. As you learned last week, another important method to visualize functions is to look at the graph. The graph of the cosine is periodic, and you can see it is symmetric in the y-axis, so the cosine is even. The graph of the sine is also periodic and point symmetric in the origin, so the sine is odd. From the graph of the tangent, you can see that the period equals pi, and that it has vertical asymptotes at the points where the cosine vanishes. Other important formulas for the trigonometric functions are sine of x squared plus cosine of x squared equals 1, which follows from the theorem of Pythagoras. You also learned how to transform a sine into a cosine and vice versa. You also recall the addition and doubling formulas. They can be very convenient to solve equations. Then we consider compositions. A composition of two functions means you first apply one function and then another. The order in which you compose can be important, as for example, 2 to the power x squared is unequal to 2 to the power x squared. Recognizing that a function is a composition can be helpful, as then you might use a substitution to turn a complicated problem in a simpler one. Typically, it is hard to identify what the graph of a composed function looks like, but when you compose a function with the linear function, the graph changes predictably. The graph of f of x plus a is equal to the graph of f, but shifted a upwards. F of x plus a shifts the graph of f a distance a to the left. A times f of x stretches the graph a factor of a in the vertical direction, while f of a times x stretches a factor of 1 over a horizontally. The compositions of a sine function with linear functions typically describe waves. 4 important aspects of a wave are its amplitude, the distance between the equilibrium position and extremal values, the period, the distance between 2 consecutive maxima, the phase, which determines when the graph first passes through the equilibrium, and the equilibrium height, which is the average height of the function. We also considered exponential functions. Exponential functions describe many processes of growth and decay. An exponential function, a times b to the power x, has base b and exponent x. Exponentiation is repeated multiplication, and thinking about it in that way explains the important rules of calculation. Using these rules of calculation, we can also define the exponential functions for exponents x, which are rational, negative, and even arbitrary real exponents. The graph of the exponential function b to the power x is increasing if b is larger than 1, and decreasing if b is smaller than 1. Moreover, for b larger than 1, the function b to the power x grows faster than any polynomial function, which is why exponential growth is sometimes used as a synonym for very quick growth. Before we define the logarithms, which are inverses of the exponential functions, we first considered inverses in a little more detail separately. The inverse of a function f does the opposite of f, that is, f inverse y equals x precisely when y equals f of x. An inverse of a function exists only if it never gives the same output for two different inputs. And you can check this by using the horizontal line test. If this happens, we call the function injective. As inverse functions interchange the role of input and output, the domain of an inverse function is the range of the original f, and vice versa. Moreover, the graph of an inverse function is obtained by interchanging the x and y axis, that is, reflecting the graph of f in the line x equals y. The logarithm base b is the inverse function of the exponential function b to the power x. If b is unequal to 1, the exponential functions satisfy the horizontal line test, so the inverse exists. For any base, the logarithm has a vertical asymptote at x equals 0. For b larger than 0, the graph is ever increasing. The rules of calculation for exponential functions translate to the rules for the logarithm. The last formula shows that you only need logarithms in one base to calculate all others. Typically, only a few bases are used. If the base is not explicitly mentioned, it should be clear from the context what the base is. Often this means the base is 10. Another common base is e, equals 2.718, etc. The base e has the special property that the derivative of e to the power x is e to the power x itself, which makes it very well suited for use in calculus. The logarithm with base e is called the natural logarithm and is usually written as ln. These were the main topics of this week. Good luck with your homework.
Hi there. This is the sound of an oboe. And this is the sound of a trumpet. The frequency and volume of these two sounds is the same, and yet you clearly hear a difference. They differ in timbre. Because of this, we can distinguish between these instruments. Now we know how to catch pitch and volume in numbers. They can be described by frequency and amplitude of the sound wave. But how to quantify timbre? This seems very elusive, and yet there is a way. If we plot the sound wave as a function of time for both the oboe and the trumpet, you already clearly see a difference in the shape of the graphs. But shape is still a bit vague. What to do? What helps here is the so-called theory of Fourier analysis. It's named after its inventor, Jean-Baptiste Joseph Fourier, a French mathematician born in the 18th century. The theory roughly states the following. Suppose you have a periodic continuous function of frequency f, then this can be written as sum of sines and cosines with frequencies f, 2f, 3f, etc. The shape of the function determines the precise amplitude of each sine and cosine. How does this work? Well, first we take a sine with the same frequency as the wave and scale the amplitude such that it best fits the wave function. What that means precisely is a bit technical. I will not explain it here. We do the same for the cosine. The sum of the sine and cosine already approximate the wave. To improve the approximation, we add a sine and cosine of double frequency, each with such an amplitude that the sum fits the wave function the best. And then we continue in this way by adding sines and cosines of 3 times the frequency, etc. The more frequencies you take, the better the shape is approximated. And in the limit, you obtain an infinite sum called the Fourier series. When it comes to sound, you need only finitely many terms in practice, since the human ear is insensitive to high frequencies. The only choices you make are the amplitudes. In fact, the shape of the graph is precisely encoded by these amplitudes. This way, we obtain a quantitative description of the shape of the graph. The theory of Fourier analysis is of fundamental importance in acoustics, optics, and signal processing, but its applications are not constrained to analyzing periodic signals. In fact, Fourier himself was not studying sound or light, but rather heat conduction through material. If you have an iron rod and heat it at some point, how does the temperature in each point of the rod change over time? You may be surprised to learn that Fourier could solve this by writing the temperature profile in the rod as a Fourier series. Do you want to know how to find a Fourier series of a given function and how it can unexpectedly help you to solve problems like heat flow? At university, you can learn all about it.
Hello. Advances in healthcare are often the result of advances in medical science combined with advances in technology. Proton therapy in the treatment of cancer is an example of such a technological advance. In Delft, the building of the first treatment center for proton therapy in the Netherlands has started. 2 Dutch medical centers, Erasmus Medical Center and Leiden University Medical Center, work together with the Delft University of Technology to realize the Holland Particle Therapy Center. Every year, about 100,000 people in the Netherlands are diagnosed with cancer. More than half of all cancer patients require treatment with radiation in order to halt the growth of their tumors, radiotherapy. Established radiotherapy techniques direct a beam of high-energy X-rays at the cancer site. In recent years, however, more and more patients around the world are treated using a beam of charged particles such as protons to eradicate the tumor.
A major challenge in treating cancer by radiotherapy is to focus as much as radiation as possible at a target, which is a tumor, but at the same time keep the radiation dose deposited in the surrounding healthy tissue as low as possible. In proton therapy, this can be done much more accurately than using X-rays. With the use of more and more advanced techniques in medicine, also mathematics becomes increasingly important. Think of questions like how to construct a 3D picture of a body to locate tumors and organs at risk. What energy and angle should the proton beams have to accurately target a tumor while leaving the surrounding tissue intact? Answering these questions involves a lot of mathematics.
For example, before the start of a radiotherapy treatment, we need to know how large the tumor is and where exactly it is located in the body. For this, doctors use an X-ray technique called X-ray computed tomography, or CT scan.
Let's look at how the technique of a CT scan involves mathematics. Suppose we want to detect a tumor in a region of tissue. For simplicity, we divide the region into small boxes. For some tumors, such as lung tumors, the density of the tumor is typically higher than in the surrounding tissue. If an X-ray passes through the tissue, it will be absorbed. The higher the density, the higher the absorption. By measuring the intensity of the outgoing beam, the total absorption in the boxes it passed through can be calculated. From that, we learn something about the density of the tissue the X-ray passed through on the way from the source to the detector. For each ray, this is the sum of the absorptions in the separate boxes. But we want to know the absorption in each separate box. To determine this, we shoot X-rays from several angles through the tissue and measure the total absorption in these angles as well. This gives a lot of relations between the quantities that we can measure, the total absorptions, and the quantities that we want to know, the absorption per box. The relations between the absorption in the boxes and the measured total absorptions are mathematical equations that can be solved. In this way, the absorption of each box can be calculated and hence a tumor can be discovered.
This example illustrates the important role of mathematical modeling. Theory provides relations between quantities that you want to know, in this case absorption per box, and quantities that you can measure, in this case the total absorption of each X-ray leaving the body. But often these relations are not explicit. You will have to solve equations to express the quantities you need in terms of the quantities that you know. Only after that you can calculate and interpret the results.
Another example. When a proton with a certain energy enters a tissue or material, it will slow down and stop, reaching a maximal depth. Physics can tell you how deep it will penetrate as a function of the initial energy. But for proton therapy, you need to know the converse. The proton has to reach a tumor, so you know the desired depth, but you want to know the energy that the proton needs to reach a tumor. So you have to solve the equation.
Equation solving is essential to extract the quantities you want to know from a model. In the following 2 weeks, we will show you techniques to attack all kinds of equations and common mistakes that you should avoid. Have fun!
Hi! If you throw a basketball, its trajectory is a parabola, that is, the graph of a second-degree polynomial. A lot of models in, for example, engineering or physics rely on polynomials, so equations involving polynomials also occur often. In this video, we look at equations of the form p1 of x is equal to p2 of x, where p1 and p2 are polynomials. For example, this equation. Graphically, this means that we try to find the x-coordinates of the intersection points of the two graphs. As a first step, we simplify the equation by bringing all the terms to the left. We see that the left-hand side here is again a polynomial. This is always the case. The equation p1 of x equals p2 of x reduces to an equation of the form p of x equals 0 for some polynomial p. That is, we try to find the zeros of p. We start with the simplest case. P is a polynomial of degree 1. Now we need to solve the equation ax plus b equals 0 for x. Well, you know what to do here. Bring b to the right-hand side and divide by a. Then the solution is x is equal to minus b over a. Next we look at equations of degree 2. First, you look whether you can factorize. For example, if we want to solve x squared minus 8x plus 12 equals 0, we factorize the polynomial as x minus 2 times x minus 6. You can check this by expanding. Now we have an equation of the form a times b is equal to 0, so that either x minus 2 is equal to 0 or x minus 6 equals 0. This gives x is equal to 2 or x is equal to 6. What if you don't see how to factorize? Well, in this case you can either use the quadratic formula or you can complete the square. Let's first use the quadratic formula. D, which is b squared minus 4 times ac, is called the discriminant. We can see from the value of d how many solutions our second-degree equation has. If d is negative, the equation has no solutions. Graphically, this means that the graph of the second-degree polynomial, a parabola, does not intersect the horizontal axis. If d equals 0, there's exactly one solution, and if d is positive, there are two different solutions. For example, we want to solve this equation, so a is equal to 3, b is minus 8, and c is equal to 4. We plug this into the formula, then we see that the discriminant is equal to 16, which is positive, so there are two different solutions, namely 2 and 2 over 3. The other way to solve a quadratic equation is by completing the square. Let's demonstrate this method with an example. Suppose we want to solve this equation, x squared plus 4x plus 1 equals 0. We want to find the square of the form x minus r squared, such that this gives the first two terms of our equation. So what we do, we expand x minus r squared as x squared minus 2r times x plus r squared. Now we see that x minus r squared minus r squared is equal to x squared minus 2r times x. So what we want minus 2r to be equal to 4. That is, r is equal to minus 2. So now we can replace x squared plus 4x by x plus 2 squared minus 4. We still have the plus 1, and this is equal to 0. Now minus 4 plus 1 is equal to minus 3. We take that to the other side. So we have x plus 2 squared is equal to 3. And now we solve this. X plus 2 is equal to plus the square root of 3, or x plus 2 is equal to minus the square root of 3. So our solutions are x is equal to minus 2 plus the square root of 3, or x is equal to minus 2 minus the square root of 3. So we found our two solutions. In general, the method of completing the square is as follows. Write ax squared plus bx plus c in the form a times x minus r squared plus s for certain constants r and s. From this form you can find the solution to the quadratic equation as in the example. Let's summarize. We can simplify an equation between two polynomials to an equation of the form px equals 0. If p is of degree 2, then there are three ways to solve the equation px equals 0. Factorize, and if you don't see how to do this, then use the quadratic formula or complete the square. Now, what can we do with equations of degree 3 or higher? We will consider these equations in the next video. Hi, welcome back. In the previous video, you saw how to solve equations of degree 1 and 2. In this video, we look at equations of the form p of x equals 0, with p a polynomial of degree 3 or higher. Let's first see if we can already say something about solutions of this equation without actually solving it. In the video on polynomials in week 1, you have seen that the graph of a polynomial of degree n intersects any line in at most n points. So the graph of p intersects the horizontal axis in at most n points. This means that the number of solutions of p of x equals 0 is less than or equal to the degree of p. For example, in the picture you can see that the equation x cubed minus 7x plus 6 equals 0 has exactly 3 solutions. Now suppose that the polynomial p has odd degree, that is, p is of the form an times x to the power n plus lower degree terms, with n an odd number. Let us assume that an is positive. We know that for x far away from 0, the polynomial behaves like an times x to the power n. So p of x is positive if x is a very large positive number, and p of x is negative if x is much smaller than 0. Since a polynomial is a continuous function, it has the intermediate value property which guarantees that p becomes 0 somewhere, as you can also see in the graph. This means that the equation p of x equals 0 has at least one solution if the degree of p is odd. Note that we can of course use the same arguments for negative values of an. If p has even degree, it can happen that there is no solution at all. For example, the equation x to the power 4 plus 1 equals 0 has no real solutions. Okay, let's now try to solve the equation p of x equals 0. You may be surprised to hear that if p is of degree 3 or 4, there are formulas to solve this. However, they are much more complicated than the quadratic formula. The question is, if we don't want to use these complicated formulas, can we still solve equations of degree 3 or higher? And yes, in some cases we can. We want to factorize the polynomial, but most of the time this is too difficult. However, sometimes we can guess a solution which gives us at least one factor of the polynomial we are looking at. For example, we want to solve x cubed minus 7x plus 6 equals 0. In this case, it is not hard to see that x equals 1 is a solution. I claim that this means that the polynomial contains a factor x minus 1. That is, the polynomial can be written in the form x minus 1 times a polynomial of degree 2. To find the coefficients a, b and c of the unknown polynomial, we expand the left-hand side and then we compare the coefficients with the original polynomial. We start with the coefficient of x cubed. This immediately gives a equals 1. Next, we look at the coefficient of x squared. This gives b minus a equals 0. We substitute a is 1 in this equation and then we find that b is equal to 1. Finally, the coefficient of x gives us the equation c minus b equals minus 7. Substituting the value of b here, we find that c is equal to minus 6. We can also compare constant terms on both sides. This gives us the equation minus c equals 6, which indeed corresponds to the value of c that we just found. So we factorized our polynomial as x minus 1 times x squared plus x minus 6. Now we continue solving the third degree equation with the factorized polynomial. The factor x minus 1 gives the solution x equals 1, which we already knew, so it remains to solve the second degree equation x squared plus x minus 6 equals 0. And we know how to do this. In this case we can factorize as x plus 3 times x minus 2. And then we obtain two more solutions, x equals minus 3 and x is equal to 2. Let's summarize what you've seen in this video. We consider the equation p of x equals 0, where p is a polynomial. If p has degree n, then there are at most n solutions. If n is odd, there's at least one solution. And if n is even, there might be no solutions at all. For solving p of x equals 0, you first try to factorize p, and if you don't see how to factorize, try to guess a solution a and extract a factor x minus a. Note that there is no guarantee that this always works. In the exercises you can practice solving equations involving polynomials. Good luck!
Welcome. We want to solve more complicated equations than just the polynomial ones. Other equations often involve ugly terms such as fractions, roots and logarithms. In this video you will learn how to deal with equations involving fractions and see the potential pitfalls. As an application of an equation containing rational functions, consider the ferry between two cities in the Netherlands, Dordrecht and Rotterdam. The ferry speed with respect to the water is v. The water flows with a speed of 8 km per hour. On the way downstream, the speed of the ferry with respect to the banks is increased with the speed of the water and becomes v plus 8 km per hour. On the way back, the speed is decreased by the same speed, thus it is v minus 8 km per hour. The distance between these two cities is 30 km. How high should v be such that the return trip takes 2 hours? You might think 30 km per hour, as we need to travel 60 km in 2 hours, but let us take a closer look. We can rewrite this question as an equation as follows. The time taken for the trip to Rotterdam equals 30 over v plus 8, as the speed in this direction was increased by the flow of the water, whereas the time for the return trip is 30 over v minus 8, as the speed is decreased on the way back. The total time is just 30 over v plus 8 plus 30 over v minus 8. And this should equal 2 hours, so we obtain the given equation. The most basic rule when solving equations is try to make things simpler. Thus the first thing we do is to simplify the equation. The ugly part of this equation is that there are fractions. To get rid of the fractions, we multiply by both denominators. That is, we multiply the entire equation by v minus 8 and v plus 8. This gives 2 times v minus 8 times v plus 8 equals 30 v plus 8 plus 30 v minus 8. I have not expanded yet, because factored expressions can be easier to work with. Only expand if you have a good reason. Notice that you obtain a quadratic equation upon expanding, so we can solve this equation using the quadratic formula, or by completing the square. No simple solution without expanding seems evident, so let's expand anyway. We obtain 2 times v squared minus 64 equals 60v. Dividing both sides by 2 and then simplifying gives v squared minus 30v minus 64 equals 0. Do you see a factorization of this polynomial? If not, you can always complete the square or use the quadratic formula. However, observing this equation equals v minus 32 times v plus 2 equals 0 shows the answers are v equals minus 2 and v equals 32. You should always check your solutions by plugging them back into the original equation. If we plug these results into the original equation, we obtain for v equals minus 2 that the equation is valid, and for v equals 32 as well. In summary, we have found our solutions by first simplifying the equation, then solving the simplified equation, and finally checking the results in the original equation. In our application, the boat must clearly have a positive speed, so the first solution is nonsense. And we see that the boat has to cruise slightly faster than 30 km per hour to compensate for the flow of the water. In the real world, the flow of the river is a little less strong and the ferry just turns its engine faster or slower to make both trips last exactly 1 hour. Recall, rational functions are quotients of two polynomials. If you have an equation involving rational functions and multiply by the denominators, you will always end up with a polynomial equation. You can solve these with the techniques of the video on polynomial equations. Thus, in principle, you can always solve these. Don't forget to end with checking your results in the original equation. In short, the method consists of simplify, solve, and check. I'll now show you why it is so important to always check your solutions. Consider the equation 2x over x minus 1 equals x plus 3 over x squared minus 1. We multiply by the denominators x minus 1 and x squared minus 1 to obtain 2x times x squared minus 1 equals x plus 3 times x minus 1. This gives the cubic equation 2x cubed minus 2x equals x squared plus 2x minus 3, which becomes 2x cubed minus x squared minus 4x plus 3 equals 0. Now we have simplified the problem to a polynomial equation. I already factored this polynomial for you. You can check the results yourselves and obtained x minus 1 squared times 2x plus 3 equals 0. Thus we find the solutions x equals minus 3 over 2 and x equals 1. Remember, we always need to check our solutions. We first check x equals minus 3 over 2 and both the left and the right hand side become 6 over 5, so this is indeed a valid solution. However, a problem occurs if we plug x equals 1 into the equation, because the left hand side becomes 2 over 0, the right hand side 4 over 0. Indeed, x equals 1 is outside the domain of both the left and the right hand side, and can therefore not be a solution to this equation. The problem occurred because we multiplied by x minus 1, which becomes 0 for x equals 1. That an equation is valid after you multiply both sides by 0 is not surprising. To summarize, the basic idea of solving complicated equations is always to simplify, solve, and check. Remember the basic idea for solving equations: simplify, solve, and check. In this video, you will learn to deal with the complexity of square roots. Consider the equation 3 equals the square root of x squared plus 3 minus x. Step 1 is to simplify, so we want to get rid of the ugliest term in this expression, the square root. How do you remove a square root? Well, by squaring, obviously. Taking the square directly in this equation will not work. The square of the right hand side contains the square of the square root, the square of minus x, but also the product of the square root and minus x. We still have a square root and did not succeed in simplifying the equation. The best option is to isolate the square root on one side of the equation and then square. This gives x plus 3 equals the square root of x squared plus 3, which, after squaring, becomes x plus 3 squared equals x squared plus 3. This is a polynomial equation, so now we know how to proceed. Expanding the brackets and simplifying gives us 6x plus 6 equals 0. The solution is x equals minus 1. We solve the equation, and the final step is to check this solution in the original equation. Remember that minus minus is plus, so this gives 3 equals the square root of 1 plus 3 plus 1, which is correct. The question arises what problems might occur when you square both sides of an equation. To show what can go wrong, let us consider the equation minus 1 equals the square root of x squared plus 3 minus x. Isolating the square, this becomes x minus 1 equals the square root of x squared plus 3. Squaring both sides gives x minus 1 squared equals x squared plus 3, and the square root is gone. Expanding brackets and bringing everything to one side shows x equals minus 1 again. But plugging in x equals minus 1 in the equation, we obtain minus 1 equals 3, which is not correct. Apparently, this equation has no solutions. How can it be that we found a false solution? We have introduced a solution to our equation at some point in our calculation. If we plug x equals minus 1 into all our steps, we can see where the problem occurred. We see that it occurred when we squared both sides of the equation. Before squaring, the equation said minus 2 equals 2, and after squaring, 4 equals 4. More generally, if the two numbers x minus 1 and square root of x squared plus 3 are equal, then their squares are also equal. Thus, any solution to the equation x minus 1 equals square root of x squared plus 3 is also a solution to the squared equation x minus 1 squared equals x squared plus 3. However, the other way around is not true. If the squares are equal, then the original numbers need not be. And this is exactly what happens in our equation. By squaring an equation, you can introduce extra solutions. Fortunately, you can easily check if this happens by plugging your solutions into the original equation. Remember to always simplify, solve, and check. Try to solve the examples in the exercises yourself.
Welcome. You may wonder, is there a general recipe that tells you how to solve a given equation? The answer is, unfortunately, no. But as you have seen in the previous videos of this week, there are techniques that you can use to attack equation and several good habits that help you avoid making mistakes. Given an equation, the following steps are important to solve it. Simplify the equation to a form that you know how to solve. Solve it and identify the solutions, and then check your solutions. In this video, I'd like to give you a general overview of these steps and summarize techniques and issues that we have encountered. To solve an equation, the main step is to simplify or reduce it to a form that you know how to solve. The idea is to transform the equation into one or several simpler equations in such a way that any solution to the new equations is also a solution to the old equation. Let's look at some strategies. The main strategy is sometimes called the balance method. Perform the same operation on both sides to simplify the equation. Let me give you a list of examples of common operations. Add or subtract the same term on both sides. In the example, we can add 3 to both sides and solve the equation. Divide by a common factor. In the example, we can divide by 1 plus square root of x. Multiply to get rid of denominators. Here, we can multiply by 1 plus x squared. Square to get rid of square roots, and more generally, to get rid of a standard function like power functions, apply its inverse if it exists. Here we use that the cube root is the inverse of the cube function. I would like to add some warnings. Be careful if you divide by a common factor. In the example, we were divided by 1 plus square root of x. This is possible since 1 plus square root of x is non-zero for all x. But consider the example x times x minus 4 equals 5 times x minus 4. As long as x minus 4 is non-zero, you can cancel this factor and obtain x equal to 5. This is a solution. But don't forget the possibility x minus 4 equal to 0, that is, x equal to 4. This is a solution as well. In general, if your equation has the form a times c equals b times c, where a, b and c are certain expressions, then you can simplify this to a equal to b or c equal to 0. Furthermore, be careful if you want to invert the function. In the example, we could get rid of the cube by applying a cube root. No problem there. But be careful when it comes to squares. For example, consider the equation x squared equal to x minus 2 squared. I've seen many students make the following mistake. To get rid of the square, we take the square root on both sides and end up with x equal to x minus 2, which has no solution. But there is a solution, namely x equal to 1, as you can check. So what's the problem here? Well, we are trying to get rid of the square function by applying an inverse function, but the square function is not invertible. In general, if a squared equal to b squared for some expressions a and b, then either a equal to b or a equal to minus b. If you forget the second, you may miss solutions. So in the example, we have to add a possibility x equal to 2 minus x, which indeed has x equal to 1 as a solution. Let's move on to other simplification strategies. You have already seen factorization. For example, the equation x squared minus 5x plus 4 can be written as x minus 1 times x minus 4 equal to 0. This implies that either x minus 1 equals 0 or x minus 4 equals 0, hence x equal to 1 or x equal to 4. This method is not limited to quadratic equations. In general, the following holds. If you can rewrite your equation as a times b equal to 0, then either a equal to 0 or b is equal to 0. Of course, this is only possible if a times b is 0. For other constants, there is no easy way to factorize. The last technique I'd like to mention is substitution. Let me show you an example. Consider the equation x to the power 6 minus 3 times x cubed minus 4 equal to 0. This is a high degree polynomial equation. However, we can rewrite it as follows. Note that x always occurs with the third power. Now we introduce a new variable, p equal to x cubed. We can rewrite the equation in terms of p. p squared minus 3p minus 4 equals 0. We call this substitution. This is a quadratic equation which you can solve using your favorite method. We obtain two solutions, p equal to minus 1 or p equal to 4. Now we can return to the original variable x. We get x cubed equal to minus 1 or x cubed equal to 4. We then take cube roots and find x equal to minus 1 or x equal to the cube root of 4, which I cannot really simplify. I cannot give you a general rule that tells you when to use which technique. This is a matter of practicing a lot, so make sure you have a look at the exercises. Once you have reduced your equation to a simple equation, or several simple equations that are standard to solve, solve everything and collect the solutions. As a last step, check your solutions by plugging them back into the original equation. Why? Well, first of all, you may have made errors, and this is the way to detect them. But even if you did not make any mistake, you may have obtained false solutions in your derivation. For example, consider the equation square root of x equal to minus 3. You can square both sides to obtain x equal to 9. This is a legitimate move, but check that x equal to 9 is not a solution of the original equation. What's the mistake here? Well, our derivation tells us that if x is a solution to the first equation, then it is also a solution to the second. But in general, the reverse does not have to be true, and in this case, it isn't. This is not a problem as long as you are aware that the new equations in your derivation may have more solutions than the first one, and you can easily identify the false solutions by simply checking. I hope that by watching this video you have an idea of useful techniques and common mistakes when it comes to solving equations, but the best way to learn it is by lots of practice, so good luck with the exercises.
Welcome to another Catch the Error video. In this video, I will show you that 1 is equal to 2. We start with the identity. We say a equals b, and a can be any number except 0. Now, we multiply both sides by a, and we subtract b squared. Now we factorize both sides. So this one becomes a plus b times a minus b. And this side becomes b times a minus b. As you can see, we have a minus b at both sides. So we get rid of that. So now we have a plus b equals b. And because we assumed a equals b, we replace b by a. So we get 2a equals a. So 2 equals 1. So now we proved that 2 is equal to 1. Clearly, we must have made an error somewhere. Did you see the error? Welcome back. Did you see where the error was made? Let's look at the calculation again. Maybe you thought that the error was in the last step, where we divided by a. But because we assumed that a was non-zero, this is allowed. Usually, dividing both sides of an equation requires care, and the mistake we did make was actually of this kind. Up to this line, we did not make a mistake, but then we removed the factor a minus b. Removing common factors is only allowed if they are non-zero. So on the next line, we must add or a minus b and 0. In this case, the last option is certainly true. Because we started with a equals b, so a minus b equals 0. And we just saw that the other option only leads to nonsense, 2 equals to 1.
Hi there. This week we looked at solving equations. You have seen useful techniques to attack several types of equations and common mistakes that you should avoid. To get you ready for the homework, let me summarize the most important topics of this week. For any equation that you encounter, remember to take the following steps: simplify, solve, and check. Simplify means reduce your equation to one or several equations that you know how to solve. There is no general recipe that tells you how to do that, but there are some useful techniques. The balance method. Try to simplify the equation by applying the same operation on both sides. Be careful, you may have to separate cases. If the equation has the form of a times c equals b times c, then this reduces to a equals b or c equals 0. Equations of the form a squared equals b squared can be reduced to a equals b or a equals minus b. Some equations can be factorized, that is, written in the form a times b equals 0. In this case, the equation reduces to two simpler equations, a equals 0 or b equals 0. Finally, you can sometimes use substitution. We write the equation in terms of new variable to simplify it. Once the equation has been reduced to several easy equations, solve them and gather the results. Finally, always check the solutions. This way, you can see whether you made mistakes. And even if you didn't, you may have picked up false solutions along the way. This is the general story. But we also looked at specific types of equations. We started considering polynomial equations. Remember that any such equation can be written as p of x equals 0, where p of x is a polynomial function. The most important cases are those where p has degree 1 or 2. The degree 1 equation has the form a times x plus b equals 0, with a non-zero. The solution is simply x equals minus b divided by a. The degree 2 equation has the form a times x squared plus bx plus c equals 0. We have seen three ways to solve it: factorization, completing the square, and the quadratic formula. In the first case, you try to write the equation as a times x minus p times x minus q equals 0. This is not always possible, but if it is, the solutions are simply x equals p or x equals q. In the second case, you try to write the equation as a x minus r squared plus s equals 0. This is always possible, and the equation can then be solved easily. Finally, you can use the quadratic formula. First calculate d, the discriminant. If d is smaller than 0, there are no solutions. If d is larger than 0, there are two solutions, given by the quadratic formula. For d equal to 0, you can still use this formula, but then the solutions go inside. So then there is only one solution. For polynomial equations of higher degree, there is no general method, but there are some techniques that can be useful. If you know a factorization, you can reduce the equation to equations of a lower degree. Sometimes you can guess a solution, x equals a. Then you can write p of x equals x minus a times q of x, where q has degree 1 less than p. Then you try to solve qx is 0. Sometimes you can use a substitution to express the polynomial in terms of a new variable and reduce the degree. But as said, a general method does not exist. However, we can say something about the number of solutions of px equals 0. Suppose p has degree n. Then there are at most n solutions. If n happens to be odd, then there is at least one solution. We then considered equations involving rational functions and square roots. The main message is, try to get rid of those. In the case of fractions, get rid of the denominator by using multiplication. If you have a root, isolate it at one side of the equation, then raise to the appropriate power to eliminate it. We have not yet treated equations involving exponential functions, logarithms, and trigonometric functions, but more about that next week. But always keep in mind our 3-step plan: simplify, solve, and check.
Hi. In this video we will introduce so-called complex numbers. As we have seen, not every equation has a solution. However, in many applications, such as vibrations of springs or in electrical circuits, these kinds of equations often occur. In order to describe the motion of such a spring or the electrical current in such a circuit, it is rather annoying that these equations don't have any solutions. For instance, it is clear that the equation x squared plus 1 equals 0 has no solutions. This becomes clear if we look at the graph of x squared plus 1. There are no intersections with the horizontal axis. In mathematics, there is a trick to overcome this difficulty. We just define a solution. In fact, we introduce an imaginary number I with the property that I squared equals minus 1. Based on this new imaginary number I, we enlarge the set of real numbers and define so-called complex numbers. Z is equal to x plus I times y, with x and y real, is called a complex number. This number consists of two parts. X is called the real part of Z, and y is called the imaginary part of Z. Here you see the notations. Now the equation z squared plus 1 equals 0 has two solutions. Z is plus or minus I. Surprisingly, we can compute with complex numbers just as with real numbers. We can add, we can subtract, we can multiply, and we can divide with complex numbers, and always the answer can be written in the form x plus I times y. Let us look how this works in some examples. If we add two complex numbers, we just add the real parts and the imaginary parts, and we end up with a new complex number. Subtraction is similar. We subtract both the real and the imaginary parts to obtain a new complex number. Multiplication is somewhat more difficult. The multiplication is defined by expanding the product as usual. So here we get minus 2 plus 3i plus 4i minus 6i squared. Now we use the convention that I squared equals minus 1 to find minus 2 plus 6 for the real part and 3 plus 4 for the imaginary part, which yields 4 plus 7i. If we want to divide two complex numbers, we expect to obtain another complex number with the property that if we multiply this by the denominator, we get a numerator. By expanding this product, this would lead to a system of two equations which can be solved. However, there is a more elegant way to do this. If we multiply both the numerator and the denominator by 1 plus 2i and expand both the numerator and the denominator, we see that the denominator gets real, and after simplifying the numerator, we only have to divide by the real number 5. And we end up with the answer minus 2 plus 3i. Now we have that every quadratic equation has two solutions in terms of complex numbers. For instance, if it can be factored, it might have two different real solutions. Z is equal to 2 and Z is equal to 3. And if it can be factored into a single square, we have only one solution. Or in fact, two equal real solutions. However, if it has no real solutions, we can complete a square. Then this square should be negative, and with the convention that minus 1 equals I squared, we find two complex solutions. Now you may think that this is just an abstract game invented by mathematicians. But it turns out that complex numbers are very useful in many parts of engineering. For example, if you want to model oscillating systems like shock absorbers in a car, or if you want to understand how electronic signals pass through a circuit, it turns out that the use of complex numbers makes calculations much easier in these situations. Are you curious how that works? You can learn all about it at university. Thanks for watching.
Welcome. If you want to know how long it takes to rise 34 meters while in the London Eye starting from the rightmost point, you have to solve an equation involving the sine of this duration. Typically, equations involving angles include trigonometric functions as sines and cosines. In this video, I will show you how to solve such equations. Let us begin with the most basic kind of equation. Consider the angle x, which satisfies sine of x equals a half. You can look in the table of the sine function and see that pi over 6, or 30 degrees, is a solution. You can also find this solution from your calculator by using the sine inverse button. This angle must thus be pi over 6, right? What else could it be? Well, consider the triangle on the slide. That is not a 30-degree angle, but its sine is also equal to a half. Let us look at the graph of sine of x. We add the horizontal line at y equals a half. The intersections of this line with the graph of sine of x are the solutions to the equation sine of x equals a half. We see that there are many solutions. Pi over 6 is just one solution. How can you find the other solutions, knowing pi over 6 is a solution? You can use the properties of the graph and of the sine function to find these others. The simplest property is that the sine is periodic, so the graph remains the same if we shift it a distance 2 pi horizontally. The red points of intersection are obtained by adding a multiple of 2 pi to the original solution. So we have 13 pi over 6 and 25 pi over 6, and to the left minus 11 pi over 6, and so on. The green point is obtained by using the symmetry of the graph of the sine upon reflecting in the line x equals pi over 2. This reflection sends x to pi minus x, so it is pi minus pi over 6 equals 5 pi over 6. The other green solutions can be subsequently found by adding multiples of 2 pi to 5 pi over 6. You can see in the graph that we have now found all solutions. We find infinitely many solutions to this equation. How can you describe all these solutions without using an infinite amount of ink? You can do this by giving a formula which describes all solutions. For example, you can write x equals pi over 6 plus 2 pi k, or x equals 5 pi over 6 plus 2 pi k, where k is an integer, either positive or negative. By plugging in all integer values of k, you obtain all solutions of the equation. For k equals 0, you obtain pi over 6 and 5 pi over 6. For k equals 1, you obtain 13 pi over 6 and 17 pi over 6, etc. You have now seen how to solve a basic equation, sine of x equals constant. A similar method works for cosine x equals constant. Find one solution using a table or a calculator, and shift and reflect this solution to get the other ones. Other equations involving trigonometric functions first have to be simplified to this form. There are two basic ways to do this. The first method is to use a substitution. Consider the example, cosine of x squared minus cosine of x equals 3/4. You can replace cosine of x by a new variable p. Using this substitution, the equation simplifies to p squared minus p equals 3/4. You should make sure no stray x's remain in your equation. You need to have an equation involving only p's and no x's, as we do here. We can solve this equation for p as p equals minus 1/2 or p is 3/2. Thus, we find that x satisfies cosine of x equals minus 1/2 or 3/2. We now have two equations of the basic form. The second equation has no solutions, as a cosine is always between minus 1 and 1. For the first equation, we need to solve cosine of x equals minus 1/2. Let us consider the graph and the table of cosine of x. There are no negative values in our table, but the cos inverse button of our calculator will still work. We can do better than using our calculator though. We can expand our basic table to x values from 0 to pi, and we know that the cosine takes negative values from pi over 2 to pi. Another symmetry of the graph shows that those values mirror the values of the cosine from 0 to pi over 2, but with a minus sign. Thus, we see that cosine of pi over 3 equals 1/2 implies that cosine pi minus pi over 3 equals minus 1/2. This gives our first answer. Reflecting 2 pi over 3 in the y-axis gives the green solution minus 2 pi over 3. The remaining solutions are 2 pi shifts of plus or minus 2 pi over 3. All solutions can thus be expressed as 2 pi over 3 plus 2 pi k, or minus 2 pi over 3 plus 2 pi k. Let us go back to our original example and use these solutions. As a final step, we check that these are valid by plugging these in our equation, using that cosine of x equals minus 1/2 for all of them. Warning! If you want to use a substitution, a common mistake is to use a substitution that leaves some x's remaining in the resulting equation. For example, if you use p equals cosine of x in the equation x times cosine of x equals 1 to get x times p equals 1, we have an x remaining. This must not happen. The final equation should only contain the new variable. In the previous example, you have used a substitution to simplify your equation to the basic form, cosine of x equals c. A second method for simplifying is to use trigonometric identities. Consider the example, cosine of x times sine of x equals 1/4. Recall that sine of 2x is 2 times cosine of x times sine of x. Thus, we recognize the result of the doubling formula for the sine in our equation. Using this, the equation simplifies to sine of 2x equals a half. We can now use that we already solved sine of x equals 1/2 to obtain that 2x equals pi over 6 or 5 pi over 6 plus 2 pi k. Dividing by 2 gives our final solution. In summary, there are two important aspects to solving equations involving trigonometric functions. To solve a more complex equation, you need to first simplify it to a basic equation. Use the substitution whenever this is possible. Remember that no x's are allowed in the resulting equation. Otherwise, you should look for a simplifying trigonometric identity. We reviewed them in week 2. Be on the lookout for things like sine squared plus cos squared and the results of doubling formulas and addition formulas, as you want to go from complicated expressions to easier ones. Sometimes you may even need to combine both methods. To solve a basic equation, sine of x equals constant or cosine of x equals constant, you first find a single solution by looking in the table or using your calculator, and subsequently use the graph of the function to obtain all other solutions. Try these techniques yourself today. In this video, we consider equations involving exponential functions and logarithms. Consider the situation from the introductory video on exponential functions. Suppose you have a bank account and you obtain 3% interest per year. How long will it take before you double your savings? This situation is equivalent to the equation 1.03 to the power x equals 2, where x is the time in years after your first deposit. This equation is an example of the simplest kind of equation involving exponentials, and you can solve it using logarithms. Indeed, the solution is log base 1.03 of 2, which is the definition of logarithm. Is this the only solution? Yes. A look at the graph of 1.03 to the power x shows that it does not take the same value twice. It is an injective function. Therefore, this equation has only one solution. To solve more complicated equations involving exponentials, the goal is always to reduce them to a simple equation of the kind a to the power p equals a to the power q, implying p equals q. There are two main techniques that can help you simplify the equation. The first technique is to change everything to a single base. For example, for the equation 4 to the power x equals 2 to the power x squared, you can rewrite everything in base 2. In this case, we can use that 4 equals 2 squared, so 4 to the power x equals 2 squared to the power x, which is 2 to the power 2x. This gives 2 to the power 2x equals 2 to the power x squared, which is an equation in standard form. Therefore, we find 2x equals x squared. The solutions are x equals 0 and x equals 2. And remember to check the solutions at the end. In this case, we get 1 equals 1 for x equals 0, and 16 equals 16 for x equals 2, so both are valid solutions. The second technique to simplify equations is by using a substitution, just as you could do with trigonometric equations. In the equation 2 to the power x plus 4 to the power x equals 6, we first change all exponentials to the same base by rewriting it as 2 to the power x plus 2 to the power 2x equals 6. Now we substitute y equals 2 to the power x and use 2 to the power 2x equals 2 to the power x squared to obtain y plus y squared equals 6. Simplifying gives y plus 3 times y minus 2 equals 0. Thus, the solutions are y equals minus 3 and y equals 2. To obtain x, we must solve 2 to the power x equals minus 3 and 2 to the power x equals 2. The first equation has no solutions, as exponentials are never negative. The second equation has solution x equals 1. Checking the solution x equals 1 in the original equation shows that we have indeed found a solution. In dealing with exponentials in equations, you want to change all exponentials to the same base, possibly make a substitution, to reduce it to a basic equation of the form a to the power p equals a to the power q. Let us now consider equations involving logs. Dealing with logarithms, you want to use the same ideas as for equations with exponentials. That is, change all logarithms to the same base, possibly make a substitution, and reduce it to a basic equation of the form log base a of p equals log base a of q. Subsequently, we can infer p equals q. However, some complications can arise. Consider the natural logarithm of x plus the natural logarithm of 2x minus 3 equals the natural logarithm of 2. All logarithms are already in the same base, so that is fine. Using the rules of calculation, this equation reduces to the ln of x times 2x minus 3 equals the ln of 2. Thus we need to solve x times 2x minus 3 equals 2. This is equivalent to 2x squared minus 3x minus 2 equals 0, which can be factored to 2x plus 1 times x minus 2 equals 0. The solutions are x equals minus 1/2 and x equals 2. Let us plug these into the original equation to check if they are valid. For x equals 2, we obtain ln of 2 plus ln of 1 equals ln of 2, so x equals 2 is indeed a valid solution. However, we can't plug x equals minus 1/2 into the equation, as both logarithms on the left-hand side take on a negative argument. In particular, x equals 2 is the only valid solution. Remember to simplify, solve, and check.
Hi there, here's another Catch the Error video. As always, I will do a calculation which contains a mistake. It's up to you to see where I make this mistake. We will solve the following equation. Log base 2 of x plus 1 squared equals 6. First, we can simplify this equation using the rules of calculation for logarithms. We can take the exponent out of the logarithm. 2 times the log of x plus 1 equals 6. Now we divide both sides by 2. The log of x plus 1 equals 3. And using the definition of the logarithm in base 2, we find that x plus 1 equals 2 cubed equals 8. So x equals 8 minus 1 equals 7. We can check that this is indeed a solution of our equation. The log of 7 plus 1 squared equals the log of 8 squared equals the log of 64 equals the log of 2 to the power 6 is 6. So we simplify the equation, solved it, and check the solution. But actually, this is not the only solution of our equation. There is another one. Can you find the solution? And do you know why we missed it here? Welcome back. We were looking for the solutions of the equation log base 2 of x plus 1 squared equals 6. Here on the slide you see the calculation we just made. The solution we missed is minus 9. We can check that this is also a solution, as you can see. We did all the steps: simplify, solve and check. So why did we miss the solution? This is because we took the exponent 2 out of the logarithm. Recall that logarithms are only defined on positive numbers, and squares are always positive. Now if we put the exponent 2 in front of the logarithm, we must consider two cases. The first case is where x plus 1 is positive, which is the case we considered. The second case is where x plus 1 is negative, but we cannot apply a logarithm to a negative number. However, x plus 1 squared is equal to minus x minus 1 squared. And if x plus 1 is negative, then minus x minus 1 is positive. So in this case, we can still take the exponent 2 out of the logarithm. And this leads to the second solution, x equals minus 9. In this particular case, we could have solved the equation without using one of the rules of calculation for logarithms. Namely, we could directly say that x plus 1 squared must be equal to 2 to the power of 6, and then solve the equation. However, when you start solving an equation, you don't always know which method will be the fastest. And actually, when an equation contains a logarithm, most of the times it will be useful to simplify the equation using the rules of calculation.
Hi there. Up until now, we have been solving all kinds of equations. As we have seen, solving an equation amounts to the question, given two functions, for what inputs are they equal? But there are also situations in which you do not want to set two functions equal, but rather compare them. For what input is the one function larger than the other? For example, think of a jet that follows some curved path. If you know a function describing the path, you can calculate the g-forces that act on the pilot as a function of time. The g-forces should not be too high, at least not for too long, otherwise the pilot may lose consciousness. We should check at what times the g-forces exceed the safety threshold. This comes down to solving an inequality. Before we turn to solving inequalities, let me review the terminology and notation. There are several inequality signs that you should know. This first expression means that A is greater than B and not equal to B. If you reverse the inequality sign, it simply means that A is less than B and not equal to B. These inequalities are also called strict inequalities. If A and B are allowed to be equal, we denote this as follows. The first notation means A is greater than or equal to B. The second means that A is less than or equal to B. Instead of less and greater, also smaller and larger are used. Having established this, we now turn to the question how to solve inequalities between functions. To make the story clearer, let's look at an illustrative example. Take the following inequality, x smaller than or equal to 4 over x. For what values of x is it satisfied? Before I tell you how to solve such an inequality, let me show you the graphs. The inequality amounts to the following question. For which x values does the green line lie above the blue one? The graph suggests that there are two intervals on which the inequality is satisfied. One unbounded interval on the left and one bounded interval. These two intervals form the solution set of the inequality. For values of x outside the set, the inequality does not hold. Now, it is important to note the following. The boundaries of the intervals are either marked by a point where both sides of the inequality are equal, or by a point where a domain problem occurs. So, to describe the solution set, we have to find these points. First, let's look at the x values where both sides are equal. That is, we solve the equation x equal to 4 over x. To get rid of the denominator, multiply both sides by x. We then obtain x squared equal to 4. This has two solutions, x equal to 2 or x equal to minus 2. You can easily check that both are indeed solutions to the equation. So equality holds for x equal to 2 and x equal to -2. Now we need to find x values where domain problems occur. This only happens at x equal to 0, since 4 over x is not defined there. The 3 points that we have found divide the real line into 4 intervals. Now the following is important. On each interval, the inequality holds either for all values of x or for no values of x, except possibly at the boundary points. So to check on each interval whether the inequality holds, it suffices to look at one point. For example, in the left interval we can try x equal to -4. You see that indeed the inequality holds. Therefore, it holds on the whole interval. In the next interval we can try x equal to -1 and see that there the inequality does not hold. So it does not hold on the second interval. We can continue in this way. Finally, we have to check the boundary points of the intervals. At x equal to 2 and x equal to -2, the inequality is indeed satisfied. At x equal to 0, the inequality is not satisfied, since the right-hand side is not defined there. We can now gather all the results to find the solutions. This inequality is satisfied for x smaller than or equal to -2, and x between 0 and 2, including 2, but excluding 0. The solution set can also be described in terms of intervals. Be aware that several ways of notation exist, but it is common to use a round bracket if the boundary is not part of the interval, and a square bracket if it is. The U-shaped symbol in the middle indicates that we take a union. The example illustrates the general method. Suppose you want to solve an inequality. Then, first, find the x values where the functions are equal and the points where one of the functions is not defined or has a discontinuity. At such points, the inequality can change from valid to invalid. These points divide the real line into intervals. Look at each interval whether the inequality holds. You can check this at one point in the interval. Finally, check at each boundary point whether the inequality holds. The solution is then the union of intervals on which the inequality holds. You may wonder what happened to the simplify, solve, check strategy that we used for solving equations. Well, the main method to simplify an equation is to apply the same operation on both sides. If you do that to an equation, it remains valid. However, for an inequality, this can be quite tricky. For example, 1 is smaller than 2. If you square both sides, it remains true. On the other hand, -3 is also smaller than 2, but -3 squared is not smaller than 2 squared. To avoid tricky problems like this, you can always use the procedure outlined in this video. Try it in the exercises.
Hi there, let's do another Catch the Error exercise. Remember the idea. I will solve an exercise for you, but somewhere I make an error. It is up to you to find out what went wrong. Let's solve the following inequality. 1 over x squared minus 1 is larger than 1. To solve it, we first look where the left-hand side and the right-hand side are equal. 1 over x squared minus 1 is equal to 1. This we can easily solve. We multiply the left-hand side and the right-hand side by the denominator. Then we add 1 to both sides. So our solutions become x is the square root of 2 and x, or x is minus the square root of 2. Let's put the solutions on a number line. You see there that there are 3 intervals where we should check the inequality. On each interval, the inequality either holds for all points or for none of the points. So we can just check at one point per interval. In the interval minus infinity to minus the square root of 2, we can take x is minus 2. we get 1 over minus 2 squared minus 1, which is 1 over 3, which is smaller than 1. In the interval minus the square root of 2 to the square root of 2, we can take the point 0, and we get 1 over 0 squared minus 1, which is equal to minus 1, which is also smaller than 1. And in our last interval, from the square root of 2 to infinity, we can take the point x equals 2, and we get 1 over 2 squared minus 1, which is again 1 over 3, smaller than 1. So for every interval, the inequality does not hold. We conclude that there are no solutions to this inequality, but that is not true. Let us calculate the left-hand side at x equals 1.2. We can see that at x equals 1.2 we get 1 over 1.2 squared minus 1, which is equal to 1 over 1.44 minus 1, which is equal to 1 over 0.44. And this is larger than 1. So you see that at x is 1.2, the left-hand side is larger than 1. Thus, x is equal to 1.2 is a solution, but somehow we missed it. What mistake did I make? Hi, let's find out what went wrong. As usual, looking at a graph clarifies a lot. In the picture you see the graph of the left-hand side of the inequality, y equals 1 over x squared minus 1 in blue, and the graph of the right-hand side, the horizontal line y equals 1 in green. The solutions to this inequality lie in the intervals where the blue graph is above the green one. Remember, the boundaries of these intervals can be points at which both sides are equal, that is, where the graphs intersect, but also at points where one of the functions is not defined or discontinuous. And now you can see what went wrong. When we tried to solve the inequality, we found the x values where the graphs intersect, but we forgot that the left-hand side is not defined at 2 points on the real line. That really matters here. You see that at these points the inequality holds on one side, but not on the other. And you can see this clearly in the graph. We relied on the graph here, but sometimes sketching the graph is not an option, because it is too difficult. But in fact you don't need graphs, as long as you keep the following in mind. Given an inequality, you must find the x values where both sides are equal. In this case, x is equal to minus the square root of 2 and x is equal to the square root of 2. But also find the x values where the functions involved are not defined or discontinuous. In this case, this happens at x is equal to minus 1 and x is equal to 1. Since the denominator of the left-hand side of the inequality is 0 there. These 4 points then divide the real line into 5 intervals. On each interval, either the inequality holds for all points or for none of them. And you can simply check at one point in each interval whether the inequality holds or not. Since we have a graph, it's even easier to tell where the inequality holds. At the intervals, minus the square root of 2 to minus 1, and 1 to the square root of 2.
Hi, welcome back. Instead of one equation in a single variable, we may also consider 2 different equations in 2 variables. Let's consider the following example. We want to calculate the points of intersection of the line given by y equals x plus 1 and the circle with radius 5 whose center is at the origin. First, we need an equation that describes the circle. Note that the circle is not the graph of a function, since there are 2 different points that have the same x-coordinate. The circle consists of all points x, y that have distance 5, the radius, to the origin. So, by Pythagoras' theorem, we have x squared plus y squared equals 5 squared, and this gives us an equation describing all points on the circle. So, if xy is an intersection point, then x and y satisfy the equations. Y equals x plus 1, that is, xy is a point on the line, and also x squared plus y squared equals 25. That is, xy is a point on the circle. We call such a set of equations in the same variables a system of equations. To solve this system of equations, we substitute the first equation into the second one. So we replace y in the second equation by x plus 1. This gives us an equation in which we only have one variable. X squared plus x plus 1 squared is equal to 25. We know how to solve such an equation of degree 2, and we find as solutions x equals 3 and x equals minus 4. Each of these solutions leads to another, simpler system of equations. Now substituting x equals 3 in the equation y equals x plus 1, we find y equals 4. And in the same way, substituting x equals minus 4 gives y is equal to minus 3. Now we found the coordinates of both points of intersection. Let's now consider the following situation. We have a stack of coins consisting of two different types of coins, say silver and gold. The height of the stack is 8 centimeters. We know that the silver coin has a thickness of 0.3 centimeters and a gold coin has a thickness of 0.2 centimeters. If x is the number of silver coins and y is the number of gold coins, then we have the equation 0.3 times x plus 0.2 times y equals 8. To make the equation look nicer, we multiply it by 10, so 3x plus 2y is equal to 80. We also weighted the coins, and the weight of the stack is 450 grams. Now a silver coin weighs 20 grams and a gold coin weighs 10 grams, so we have the equation 20x plus 10y equals 450. In this case, we divide by 10 to make the equation look nicer. The question is, of course, how many silver and how many gold coins have we got here? The answer is obtained by solving this system of equations. In the previous example, with the line and the circle, the first equation was of the form y is equal to a function of x, and we could substitute this into the second equation. Here we can do something similar. We first solve the second equation for y, which gives y equals 45 minus 2x, and then substitute into the first one. This gives us an equation in only one variable. Expanding the brackets, we obtain 90 minus x equals 80. Solving this gives the solution x equals 10, and putting this back into the equation y equals 45 minus 2x, we see that y equals 25. So we have 10 silver coins and 25 gold ones. The system of equations in this example also has a graphical interpretation. The equation 3x plus 2y equals 80 defines a line, namely the graph y equals 80 minus 3x divided by 2, the blue line here. The equation 2x plus y equals 45 defines the green line, which is the graph y equals 45 minus 2x. The solution that we found is the point of intersection of these two lines. We just solved two systems of equations using the substitution method. Solve the simplest of the two equations for y, substitute the expression for y into the second equation to obtain an equation only in x. Then solve this equation for x and substitute the result in the expression for y. Instead of first solving for y, you can also first solve for x. The substitution method is usually a good method to solve a system of two equations in two variables. However, the following example shows that you should be very careful with this method. Suppose we want to solve this system of equations. X times y equals 2x and x squared plus y squared equals 1. We solve the first equation for y, which gives y equals 2. Substituting this into the second equation leads to x squared plus 2 squared equals 1, and we conclude that there are no solutions. But actually, we missed a solution. Plug x equals 0 and y equals 1 into both equations to see that this is a solution to the system. So why did we miss this solution? This is because the equation xy equals 2x has solutions y is equal to 2 and x is equal to 0. Plugging x equals 0 into the other equation gives y squared equals 1, so that y equals plus 1 or minus 1. So our system of equations has two solutions, x equals 0 and y equals 1, and x equals 0 and y equals minus 1. The substitution method can also be used for systems of 3 or more equations with 3 or more variables, but this is often much work.
Welcome to the summary of week 4, in which I will give an overview of the topics treated this week. First of all, remember the 3-step plan from last week. If you want to solve an equation, you should simplify, solve, and check. The first topic of this week is equations involving trigonometric functions. First, you try to simplify such an equation to an equation of the form sine of x equal to c or cosine of x equal to c. To do this, use an appropriate substitution or trigonometric identities like double angle formulas, addition formulas, or sine of x squared plus cosine of x squared is equal to 1. Sometimes it may even be necessary to use both methods. To solve the simplified equation, you should find a single solution using a table or a calculator, and then use the graph to obtain all the other solutions. Then we consider the equations involving exponential functions and logarithms. If you encounter an equation involving exponential functions, you always want to reduce it to an equation of the form a to the power p is equal to a to the power q, which implies p equals q. There are two main techniques to simplify the equation. First, you change all exponentials to the same base, and then, possibly, you use a substitution. To solve an equation involving logarithms, the ideas are basically the same. You always want to reduce to an equation of the form log base a of p is equal to log base a of q, which implies p is equal to q. To get the equation in this form, you first write all logarithms in the same base, and possibly you make a substitution. The next topic was solving inequalities. We want to find out for which values of x the graph of f is below the graph of g. The general method to solve such inequalities is the following. First, find the x values where the functions are equal, and the points where one of the functions is not defined or has a discontinuity. At such points, the inequality can change from valid to invalid. Then, these points divide the real line into intervals. Look at each interval whether the inequality holds. You can check this at one point in the interval. Finally, check at each boundary point whether the inequality holds. The solution is then the union of intervals on which the inequality holds. The last topic of this week was systems of equations. That is, we want to solve a set of two equations in two variables. This is useful, for instance, if you want to find the intersection points of a line and a circle. To solve such systems of equations, you can use the substitution method. Solve the simplest of the two equations for y, substitute the expression for y in the second equation to obtain an equation only in x. Then solve this equation for x and substitute the result in the expression for y. Instead of first solving for y, you can also first solve for x. These were the topics of week 4. Good luck with your homework.
Hi! In this week you practiced with inequalities and systems of equations. In this video you will see how these can be useful in an optimization problem. Suppose you really like these Delft blue cups and towels and you would like to sell them. Maybe making pottery is not really your thing, so you decide to make them with your 3D printer. Of course, you want your profit to be as high as possible, so you want to know how many cups and how many towels you should make. Now, you cannot make an unlimited number of them. There are some limiting conditions that you need to take into account. First of all, the tiles and cups are printed with blue and white clay. Let's say a tile consists of 30% blue and 70% white, and a cup consists of 40% blue and 60% white. If T is the number of tiles you make and C the number of cups, and if each cup or tile takes exactly 0.1 kilograms to print, the amount of blue clay you need is equal to 0.1 times 30% of T plus 0.1 times 40% of C. And in the same way you find the amount of white clay that you need. But let's say you only have 10 kilograms of blue clay and 20 of white. Then we have the following constraints. 0.03 T plus 0.04 C is less or equal 10, and 0.07 times T plus 0.06 times C is less or equal to 20. These inequalities say that the total amount of blue or white clay that you use is less than the amount you've got. To maximize the profit, you need to know what the profit is on one cup and on one tile. Let's say the profit on a tile and a cup is both €1. Then the total profit is the number of tiles and the number of cups that you sell. So we need to solve the following problem. Maximize the function P equals T plus C under the constraints that we just found. How can we do this? Well, first we make a picture of all the inequalities. Let's start with the inequality for the blue clay. If we remove the less than sign, we get the equation of the blue line. Then all points T, C satisfying the inequality are below the blue line. Note that in the picture we also use that the number of cups and tiles is non-negative, that is, T is greater equal 0 and C is greater equal 0. The inequality corresponding to the white clay gives the area below the white line. Now the points in the bright yellow area correspond to the number of tiles and cups that you can actually produce. Next, we also draw lines representing the profit P. Suppose you want P to be equal to 100, then this corresponds to the line T plus C equals 100, which is the orange line here. The line corresponding to P equals 200 is parallel to the line corresponding to P equals 100. So you see that shifting this line upwards corresponds to making more profit. So you want to shift this line upwards as far as possible. But the line needs to intersect the yellow area, otherwise it corresponds to profit that you cannot actually make. So from the picture you see that the highest profit you can make, which is 300 here, corresponds to the intersection point of the white and blue lines. You can find the intersection point by solving two equations, and this gives T equals 200 and C equals 100. So these are the number of tiles and cups that you need to make to maximize your profit. The method that we just used is an example of an optimization method called linear programming. In actual problems, for example, in planning of routes for ambulances, there might be thousands of variables and conditions, but the underlying idea remains the same.
Roller coasters. Do you love them? Do you like to feel the G-forces and scream out loud? Or are you too scared? If I see those massive constructions of roller coasters, I can't help but wondering, how do they invent these rides? And how do you make a roller coaster spectacular but safe?
I love roller coasters too. The design of a roller coaster demands both creativity and thorough calculations. These calculations are strongly related to the topic of this week, differentiation. To construct a roller coaster, you have to deal with finding a good trade-off between different requirements. For a thrilling ride, you want high speed and acceleration. But for safety reasons, you want to limit the G-forces that people will experience. We call this an optimization problem. Differentiation plays a very important role in solving those problems.
Another important aspect is that a roller coaster track is constructed from basic segments. These segments need to be connected in such a way that the track is smooth and doesn't have any kicks or bumps. The slope and direction at the connection point of any pair of segments should coincide. If not, the ride would be very unpleasant. Mathematically, this means precisely that the track should be differentiable. This gives another aspect of roller coaster design where differentiation comes in.
So, Two of the most important ingredients for building a great roller coaster ride are slope and speed. But what is slope and what is speed exactly? Even to define slope and speed, we need the concept of differentiation. This week, you will learn about differentiation and its many applications. Enjoy the ride. Hi. In the roller coaster video, two questions were raised. How to determine the slope of the roller coaster track and how to determine the speed of the roller coaster kart. The funny thing is that both questions can be answered using differentiation. Let me show you how. Let us start with the concept of slope. How is it defined? First, we look at a straight but inclined part of the roller coaster track. When a kart moves from point P to point Q, there is a corresponding horizontal displacement, delta x, and a vertical displacement, delta y. The slope is simply defined as delta y divided by delta x. For example, if delta x equals 10 meter and delta y equals 5 meter, the slope is 0.5. Because the line is straight, it does not matter where we take P and Q. If we take Q twice as far, delta x will double, but so will delta y, so the slope remains the same. We can even take Q on the other side of P. Then delta x is negative, say minus 4 meter. Delta y then equals minus 2 meter, so the quotient remains the same. As you would expect, the slope is a measure of steepness. If the track is steeper, then for a fixed delta x, the corresponding delta y will be larger, and so the slope will be larger. Finally, descent corresponds to a negative slope. If delta x is positive, say 10 meter, the corresponding delta y will be negative, say minus 4 meter. Therefore, the slope will be negative, in this case, minus 0.4. What if the track is not straight? Suppose we want to determine the slope at point P. If we zoom in at the track near P, the track will look approximately straight. So if we take Q close to P and take the quotient of the displacements, we get an approximation of the slope of the track. To improve the approximation, we move Q to closer to P. The quotient of delta y and delta x approaches a limit value. This value is, by definition, the slope at P. Now let us consider the concept of speed. First, suppose that the speed of the roller coaster kart is constant on some part of the track. In that case, you can determine it by measuring the distance, delta x, traveled during a time interval delta t, and then take the quotient. For constant speed, it does not matter what time interval we take. Now, suppose that the speed is not constant, and we want to determine the speed at time t. Again, we can measure the distance delta x traveled during a time interval delta t, and then take the quotient. This will give us the average speed on the time interval, but not the speed at time t. However, if the time interval is small, the speed is approximately constant during the time interval. So the speed at time t is approximately equal to delta x divided by delta t. To make the approximation better, we take delta t smaller and smaller. The quotient of delta x and delta t then approaches some limit value, this speed at time t. We see that both slope and speed can be determined by taking the limit of a quotient. That is exactly what differentiation is. More precisely, suppose a function f and a point with x-coordinate equal to a are given. If the x-coordinate changes from a to a plus delta x, the function value changes. The vertical increase is equal to f in the point a plus delta x minus f at the point a. The horizontal increase is simply equal to delta x. The quotient of these two is called a difference quotient. Now, we can take the limit of delta x to 0. If this limit exists, the number you obtain is called the derivative of f at x equal to a. It is denoted by f prime of a or df divided by dx in the point a. The whole process of determining the derivative is called differentiation. If you look at the graph, Both the difference quotient and the derivative have a geometric interpretation. The difference quotient is precisely the slope of the line connecting the points P and Q on the graph. Now, if we let delta x go to 0, you see that this connecting line approaches a limiting position. The slope of this limiting line is precisely the derivative of f at a. The limiting line itself is called the tangent line to the graph at the point P. It is the unique line with the property that it passes through the point P and has the same slope as the graph in that point. Now let us return to the original questions. What is slope and what is speed? We have seen that both slope and speed can be interpreted as derivatives. Slope as the derivative of vertical position y as a function of horizontal position x. Speed as the derivative of position x as a function of time t. The definition in terms of the limit of a difference quotient may seem abstract, but it provides the basis for many measuring devices. For example, a bicycle computer can measure the time it takes for the wheel to make one revolution. In this case, delta t is the time measured, delta x is the circumference of the wheel. The current speed is approximated by delta x divided by delta t, the difference quotient. Usually this approximation is sufficiently accurate. What if you want to calculate derivatives exactly? Taking limits every time can be cumbersome. In the next section, you will learn how to deal with this. But first, let's practice with the concept. Good luck.
Would you like to know how you can calculate the derivative of all functions you will ever encounter? In this video, we'll set up the basic framework which will allow you to do so. This week, we have learned a mathematical definition of the derivative as a limit. Calculating derivatives using this limit is typically quite difficult. Therefore, we like to have simpler rules of calculation so we can calculate the derivatives of more general functions than just the standard ones. What functions do we encounter? Well, we know standard functions such as polynomials, the sine, and the exponential function. And we have rules to combine them, such as taking the product of two functions. Subsequently, we can create more complicated functions by taking combinations of standard functions. For example, e to the x times sine of x. And by taking more complicated combinations and even more complicated combinations. The grand plan for calculating derivatives is the following. First, you learn the derivatives of the standard functions. And second, you learn the rules to calculate the derivative of combinations of standard functions, such as the chain rule. For each method of combining functions, we want the rule which tells us the derivative of the combination in terms of the simpler ingredients. In the future, whenever you need to differentiate a non-standard function, you can analyze it to determine how it is a combination of standard functions, apply the rules, and use the derivatives of the standard functions to obtain its derivative. Together, this implies we need to know just a few derivatives and a few rules to be able to determine the derivative of infinitely many functions. If you learn any new standard functions at university, you always want to discover what its derivative is, so you can still play this game for functions which involve this new standard function. Likewise, for new methods of combining functions, you will want to figure out what this implies for the derivative of the combination. You will learn the rules of combination in the next video, but first you can review the derivatives of standard functions by doing the exercises. Good luck! Having trouble remembering all those rules for taking derivatives? In this video, we'll try to help you by giving you examples to remember them by. Whenever an abstract mathematical formula arises, you want to think of a concrete example which illustrates the formula. It's a good exercise to try to come up with your own examples. Let us start with the most basic rule of calculation, multiplying a function by a constant. Consider a car on a roller coaster and let us measure the distance it has traveled in meters as a function of time measured in seconds. The derivative of this function is the speed in meters per second. If we change the unit of distance to feet, we know that there are 3.3 feet in a meter, so the number of feet traveled is 3.3 times the number of meters traveled. Likewise, the number of feet per second is 3.3 times the number of meters per second. This illustrates that the derivative of a constant times a function equals that constant times the derivative of the function. We can also see this visually if we look at the graph of f. The graph of 2f has a slope twice as high as that of f. Next, we consider the addition rule by looking at someone walking in a moving train. The speed of the boy with respect to the track equals the sum of the speed of the train and his walking speed. That is, the derivative of f plus g equals f prime plus g prime. The product rule, sometimes also called Leibniz's rule, is the first of the two most important rules of calculation. Consider a pyramid. If we take a cross-section at a distance x from the top, we obtain a rectangle with width wx and length lx, depending on this distance x. The area of the rectangle is the product wx times L of x. Let us now consider the derivative of this area, which is the rate at which the area increases if we look a little further down the pyramid. Having x increase to x plus delta x increases both the width and the length. The extra area can be split in three parts. The yellow part equals the width times the change in length. The green part is the length times the change in width. And the small purple rectangle is the change in length times the change in width. Now, observe that the change in width is approximately the derivative of the width times delta x. And similarly for the change in length. We can use this to calculate the area of the three rectangles. If we now look at the rate, we see that the derivative of the area equals the width times the derivative of the length, plus the length times the derivative of the width. The limit of the area of this small purple rectangle becomes small as delta x goes to 0, even after dividing this area by delta x. Thus, if the change in height tends to 0, it does not contribute to the derivative. As an example of how to use this rule, we now calculate the derivative of x squared times sine of x. This equals the derivative of x squared times sine of x plus x squared times the derivative of sine of x, which is equal to 2x sine of x plus x squared times cosine of x. In this video, we have illustrated the following three rules of calculation. Multiplying a function by a constant multiplies the derivative by the same constant. The addition rule tells you that the derivative of a sum is the sum of the derivatives, and the product rule gives the derivative of the product f times g as f times g prime plus f prime times g. In the next video, we will have a look at the chain rule. See you there. Welcome back. In these videos we review the rules of calculation for differentiation. In the previous video we considered the product rule. The other very important rule of calculation is the chain rule. Consider a diver in the sea. To avoid decompression sickness, the rate at which the diver can return to the surface must be restricted. The issue is not so much the change in height, but the change in pressure. During the diver's ascent, the pressure is a function of the depth, x, which itself is a function of time. Thus, we are interested in the derivative of the pressure as a function of time. If we consider a short period of time, delta t, then the change in pressure equals the change in pressure per meter times the change in depth in this short time. Taking the limit as delta t goes to 0, we find that the change in pressure per second equals the derivative of the pressure as a function of depth times the derivative of the depth as a function of time. In the formula, this becomes f of g of x prime equals f prime of g of x times g prime of x. Notice that the derivative of pressure as a function of depth is typically almost constant, so the rules on the speed of ascent are typically given just in terms of speed. There are two frequent mistakes made when using the chain rule. The first one is to forget the factor g prime of x. The second one is that we need to evaluate the derivative of the outer function f at the value g of x and not at x. You can remember this using the diver. Where should we evaluate the derivative of the pressure as a function of depth? Well, obviously, at the depth we are currently at, which is given by the value of the inner function. As an example, we now calculate the derivative of ln of x squared plus 1. The derivative of the natural logarithm equals 1 over x. So we see for the derivative of ln x squared plus 1 that we obtain 1 over x evaluated at x squared plus 1 times the derivative of x squared plus 1, which is 1 over x squared plus 1 times 2x. Finally, the derivative of f over g is often given as an extra rule, the quotient rule. It's easiest to think of this as a combination of the chain rule and the product rule. Indeed, f over g equals the product of f of x and 1 over g of x. So using the product rule, we obtain that this equals f prime of x times 1 over g of x plus f of x times the derivative of 1 over g of x, which is f prime of x over g of x plus f of x. And to calculate the derivative of 1 over g of x, we use the chain rule, so we need to know the derivative of 1 over x, which is the derivative of x to the minus 1, so we get minus 1 times x to the minus 2, which is minus 1 over x squared, so we get minus 1 over gx squared times the derivative of g. Putting everything under the same denominator, we obtain f prime of x times g of x minus f of x times g prime of x divided by g of x squared. Remembering the quotient rule this way, make sure you never get the wrong sign in this rule again. For example, the derivative of x over x squared plus 1 equals 1, the derivative of x over x squared plus 1, plus x times the derivative of 1 over x squared plus 1, which is minus 1 over x squared plus 1 squared times the derivative of x squared plus 1, which becomes x squared plus 1 over x squared plus 1 squared plus x times minus 1 times derivative of x squared plus 1 is 2x over x squared plus 1 squared, which we can simplify to 1 plus x squared minus 2x squared is 1 minus x squared over x squared plus 1 squared. Now, have a look at the exercises. In the second video on standard derivatives, we consider the trigonometric functions. We only look at the derivation of the derivative of the sine, as the same story works for the cosine. Let us first just graph the sine function. Remember that in calculus we calculate our trigonometric functions using radians. Thus the maximum of the sine occurs at pi over 2. What would the derivative of the sine look like? Well, the sine starts off going up, so the derivative is positive. Subsequently, the derivative is getting smaller and smaller until it passes the x-axis at pi over 2, where the sine has a maximum. Then the derivative is negative as the sine is decreasing, with its lowest value at pi, where the derivative is mostly going down. Then it goes up again as the sine is curving upwards and passes the x-axis again at 3 pi over 2, where the sine has a minimum. Then it increases again until 2 pi, and subsequently we see that because the sine function is 2 pi periodic, the derivative also repeats itself. We have now drawn the graph of the derivative. Does it look like a function we know? Indeed, it looks like the cosine. Notice that we can easily remember it is plus cosine, as the derivative must be positive at x equals 0, since the sine is going up. Let us now consider this more precisely. As we know, the sine is the y-coordinate of the point on the unit circle for an angle phi. So we need to know what happens to this y-coordinate if we slightly increase the angle from phi to phi plus delta phi. To better see the change in y-coordinate, we add a little triangle over this little arc. This is a very small triangle, so let us zoom in. Now, we know two things. Because the arc is so small, the circle looks like a straight line in this zoomed-in picture. Just like the surface of the Earth appears flat for us, even though it's a big sphere. Recall that the length over an arc of the unit circle equals the associated angle in radians by definition. So the length over this arc equals delta phi. It is, moreover, approximately the same as the length over a straight line with the same endpoints. This straight line is the hypotenuse of a right-angled triangle, one of whose sides is a change in y-coordinate. The change in y-coordinate can then be expressed as the length of the hypotenuse times the cosine of alpha, which approximately equals delta phi times cosine of alpha. It remains to find the angle alpha at A, which is the angle between a vertical line and the tangent line to the circle. Let us zoom out again to determine alpha. Note that the tangent line to the circle is always orthogonal to the line from the origin. Moreover, the angle below A equals pi over 2 minus phi, so the angle alpha equals pi minus pi over 2 minus pi over 2 minus phi equals phi. We conclude that the change in y-coordinate equals approximately delta phi cos phi. Plugging this in the definition of the derivative, we find that the derivative of the sine equals the limit of delta phi cos phi over delta phi, or the cosine of phi. Remember our grand plan for calculating difficult derivatives? It had two ingredients: knowing the derivatives of standard functions and knowing some rules of calculation. In these videos, we will tackle the derivatives of some standard functions. We will use the derivative of the exponential function to calculate the derivatives of x to the power p. The trick we will use here applies to any ugly function involving exponentials, so you can use it too. Let us recall the definition of the derivative as the limit of a difference quotient. While the idea is not to use this formula in actual calculations and use standard derivatives and rules of calculation instead, we have to use it to calculate the derivative of our standard functions. Let us first consider exponential functions. We plug an exponential function, f of x equals a to the power x, in the formula for the difference quotient. This gives a to the x plus delta x minus a to the x over delta x. But the rules of calculation for an exponential show that this also equals a to the power x times a to the delta x minus a to the x over delta x. Taking a to the x apart, we find that this equals a to the x times a to the delta x minus 1 over delta x. Notice that the right part is exactly the difference quotient for a to the x at 0. Taking the limit as delta x goes to 0, we see that the derivative of a to the x at x equals a to the x times the derivative at 0, a constant times a to the x. This constant depends on a. Looking at the graphs of different exponential functions, we see that the derivative at 0 is very small and positive if a is slightly more than 1, whereas we can make it as large as we want by increasing a. At some point, the constant will be equal to 1, so the graph will be tangent to y equals x plus 1. The corresponding value of a is called e. The value of e equals 2.718, etc. So in fact, the derivative of the standard function e to the x is e to the x by definition. For a to the x for other values of a, we now use that a to the x equals e to the x ln a and use the chain rule. E to the x ln a. This gives that it's equal to the derivative of e to the x at x ln a times the derivative of x ln a, which is equal to a to the x times ln a. Let us now consider the derivative of ln x. Ln x is the inverse function of e to the x, and we can obtain its derivative by considering the equation x equals e to the ln x. The derivative of x equals 1. Thus that is the result of applying the chain rule to the right-hand side. So 1 equals the derivative of e to the ln x equals the derivative of e to the x at ln x times the derivative of ln x. As e to the ln x equals x, this gives 1 equals x times the derivative of ln x, so that we find that the derivative of ln x equals 1 over x. The trick of using the exponential function to calculate derivatives of a function involving exponents can also be used if the x dependence is in the base. Thus we find that the derivative of x to the power p for arbitrary p, not just integers, can be calculated by writing x to the p equals e to the p ln x. Using the chain rule, we obtain that the derivative of x to the p equals the derivative of e to the x at p ln x times the derivative of p ln x, which equals e to the p ln x times p over x, which is x to the p times p over x equals p times x to the p minus 1. These calculations show that you don't have to remember all standard derivatives, as you can derive some from others. However, we use the derivative of x to the p often enough that it is easier to just remember that it is multiply by exponent and decrease exponent by 1 than to remember its derivation. However, if you're like me and often forget whether the derivative of 2 to the x is 2 to the x times ln 2 or 2 to the x divided by ln 2, you can always fall back to remembering this derivation to get it right. Now, try to use the trick to rewrite complicated exponentials as e to the something to calculate some derivatives yourself. Would you like to know how you can calculate the derivative of all functions you will ever encounter? In this video, we'll set up the basic framework which will allow you to do so. This week, we have learned a mathematical definition of the derivative as a limit. Calculating derivatives using this limit is typically quite difficult. Therefore, we like to have simpler rules of calculation so we can calculate the derivatives of more general functions than just the standard ones. What functions do we encounter? Well, we know standard functions such as polynomials, the sine, and the exponential function. And we have rules to combine them, such as taking the product of two functions. Subsequently, we can create more complicated functions by taking combinations of standard functions. For example, e to the x times sine of x. And by taking more complicated combinations and even more complicated combinations. The grand plan for calculating derivatives is the following. First, you learn the derivatives of the standard functions. And second, you learn the rules to calculate the derivative of combinations of standard functions, such as the chain rule. For each method of combining functions, we want the rule which tells us the derivative of the combination in terms of the simpler ingredients. In the future, whenever you need to differentiate a non-standard function, you can analyze it to determine how it is a combination of standard functions, apply the rules, and use the derivatives of the standard functions to obtain its derivative. Together, this implies we need to know just a few derivatives and a few rules to be able to determine the derivative of infinitely many functions. If you learn any new standard functions at university, you always want to discover what its derivative is, so you can still play this game for functions which involve this new standard function. Likewise, for new methods of combining functions, you will want to figure out what this implies for the derivative of the combination. You will learn the rules of combination in the next video. But first, you can review the derivatives of standard functions by doing the exercises. Good luck!
Hi there! So far we took derivatives of many different functions. But you might wonder, can we differentiate any function at any point? The answer turns out to be no. Now we will look at what might go wrong. Remember that the function is differentiable at the point a if the limit, as delta x goes to 0, of the following difference quotient exists. F of a plus delta x minus fa divided by delta x. By exist, we mean that the limit must be exactly one real number. Graphically, the difference quotient is the slope of the green line, and in the limit it approximates the slope of the tangent line. So a function is not differentiable at a if this limit does not exist, meaning that there is no tangent line at a, at least not with a finite slope. Let's look at a few examples. Our first example is a function with a jump at a, so a non-continuous function. Let's see if we can approximate a tangent line at a. First we take delta x positive, and then the difference quotient is the slope of the green line. Now, if we let delta x go to 0, we see that the green line approximates a horizontal line. This is our candidate for the tangent line. Okay, now we do the same with a negative delta x, and you see what goes wrong. The green line does not approximate the same horizontal line that we had before. So in this case, the limit of the difference quotient does not exist, and we conclude that the function is not differentiable at the point a. Next we look at the function whose graph has a kink in it, the absolute value of sine of x, which has a kink at 0. We do the same as in the previous example. We approximate the tangent line with delta x positive, and then with delta x negative. We see that we get different lines again, so this function is not differentiable at 0. The last function we look at is the cube root of x. We can do the same as before. Approximate the tangent line at 0 by first taking delta x positive and then negative. But nothing seems to go wrong. The graph has a tangent line at x is 0. The problem in this case is that the tangent line is vertical, so the slope of the tangent line is infinite. Recall that we said that the function is differentiable at a if the limit of the difference quotient exists. That is, it must be a real number. Well, in this case, the limit equals infinity, which is not a real number. So the limit does not exist, and the function is not differentiable at 0, even though the graph has a tangent line. So far we have seen the following types of non-differentiable functions: non-continuous functions, functions with a kink in the graph, and functions whose graph have a vertical tangent line. These are the types of non-differentiable functions that you will encounter the most. There are more types of non-differentiable functions, however, you will not encounter them very often. So remember, not all functions are differentiable.
Welcome back. A roller coaster track has highest points and lowest points. If we know a function that describes the track, how can we find these points? This simple question, how to find minima and maxima of a function, has numerous other applications because it has to do with optimization. Think of economics. A firm wants to know at which output the profit is maximal. Or physics. The stable states of a mechanical system are precisely those for which the energy is locally minimal. Or think again of our roller coaster example. The speed may not be too high due to safety and cannot be too low either, because then the cart may get struck on the track. So when you are designing a roller coaster, you have to know what the minimal and maximal speed of the cart will be. In this video, you will learn how differentiation can be used to deal with such optimization problems. Let me first recall some terminology. We say function f has a global maximum at x equal a if all function values are smaller than or equal to f of a. Similarly, we say f has a global minimum at x equal b if all function values are larger than or equal to f of b. The name global suggests that there are other types of maxima and minima. Well, there are. We say that f has a local maximum at x equals c if fc is the largest value that f attains on some interval around x equals c. Similarly, we say f has a local minimum at x equals d if f of d is the smallest value that f attains on some interval around x equal to d. Note that this also holds for the global maximum and minimum. Those are special cases of local maxima and minima. By the way, sometimes I get tired of saying maximal values and minimal values and simply call them extremal values. What do these extremal values have to do with differentiation? Well, recall the following. If a function is differentiable and the derivative is positive, then it is increasing. If the derivative is negative, it is decreasing. Now, at a local maximum or minimum, f is neither increasing nor decreasing, so the derivative is precisely 0 at those points. Indeed, let's look at a local maximum in the graph in the picture and zoom in. If you pass over a maximum from left to right, then just before the maximum the slope is positive, and right after the slope is negative. Precisely at the local maximum the slope is 0. Based on this, you may suspect the following. Given a function f and a point a where f has an extremal value, the derivative of f at a equals 0. Let me stress here that this is not always the case. Look at the following example, the absolute value of x. This function is has clearly a minimum at x equal to 0. But what is the derivative there? As we have seen in the previous video, the derivative does not exist there. So we see maxima and minima can also be attained at points where the derivative does not exist. Okay, so now you may suspect the following. In local maxima and minima of f, either the derivative vanishes or it does not exist. Even that is not always the case. For example, look at this picture of the famous Gateway Arch in St. Louis, USA. Its height, as a function of horizontal position, is a differentiable function. At the highest point, you see that the derivative of this function is 0. Nothing extraordinary there. But what about the lowest points? Clearly, the lowest points are at the feet of the arch. The height function is differentiable there, but the derivative is not equal to 0. So what's going on here? Well, we are talking about points at the boundary. At boundary points, a function can have a local maximum or minimum without vanishing derivative. Okay, let's gather what we have seen. If f attains a local maximum or minimum at x equal to a, then either f prime of a equals 0, or f is not differentiable at x equal to a, or x equal to a is a boundary point of the domain of f. And this is indeed the full story. Let me introduce some extra terminology. Points on the horizontal axis where the derivative of f is 0 are called critical points. Points where the derivative does not exist are called singular points, and if a point is at the boundary of the domain of f, it's called, naturally, a boundary point. A warning is in place here. It is a common mistake to use this result in the wrong way. It says that if f is locally extremal at x equal to a, then x equal to a must be a critical point, singular point, or boundary point. But the other way around is not necessarily true. For example, if the derivative is 0 at some x, then the function does not necessarily have a local minimum or maximum there. A standard example is the function x cubed. The derivative is equal to 3 times x squared, which is 0 at x equals 0. So this function has a critical point at x equal to 0, but it has no extremum there. It is increasing for both x smaller than 0 and x larger than 0. Similarly, a function can have singular points which are neither local at maximum nor a local minimum, as the example shows. Keep that in mind. Let me summarize. If you want to find local extrema of a function, first find the critical points, singular points, and boundary points. If the function has local extrema, then it must be at those points. So we have limited our search from the whole domain of f to a limited set of points. But keep in mind, we still have to investigate the function at each of those points to see whether it has a local maximum or a local minimum, or neither. You will see tips and tricks for that in the rest of this subsection. Let's practice.
Hi, we're going to do a Catch the Error video again. Just a reminder, in this video we will give you a problem that's not correctly worked out. Your task is to find our mistake, so pay attention and catch that error. Consider the function f of x equal to x cubed minus 3x on the closed interval from minus 3 to 3. On this interval, the function has a global minimum and maximum value. What are they? Well, what were the steps of finding the global extreme values of a function? The first step, determine the derivative. The second step, find the critical points, so setting the derivative to 0 and solving for x. When we have done this, we can find out if we have found a minimum or a maximum value of f at a point A by making a number line of the derivative of f. The last step is to find out the function value of these points, so we get our extreme values of f. Let us first determine the derivative of f. The derivative becomes 3 times x squared minus 3. We know that the extreme values can occur at critical points, so we set the derivative equal to 0, and we solve for x. So we set the derivative equal to 0. Well, this is quite an easy function. So we take 3 to the other side, divide by 3, and we get our values. X is plus minus 1. Okay, so let's see if these points correspond to minimum or maximum values of f. We can do this by making a number line of the derivative of f to see if the function is increasing or decreasing around our critical points. So we make a number line where we set minus 1 and 1, where the derivative equals 0. At 0, the derivative is equal to minus 3. So it's negative there. It's decreasing. At 2, the derivative equals 3 times 2 squared minus 3, which equals 9. So the function is increasing there. At minus 2, we have 3 times minus 2 squared minus 3, which also equals 9. So the function is also increasing at minus 2. This gives us increasing, critical point, decreasing, critical point, increasing. We can now see that our function f has a maximum value at minus 1 and a minimum value at plus 1. To find our extreme values, we now only need to compute the function values. F of minus 1 equals minus 1 cubed minus 3 times minus 1, which equals 2. F of 1 equals 1 cubed minus 3 times 1 equals minus 2. So our maximum value is 2, and our minimum value is minus 2. So to conclude, f has a global maximum value of 2 at x equals minus 1, and a global minimum value of minus 2 at x equals 1. But the value of f at x equals 3 is equal to 3 cubed minus 3 times 3, which is 27 minus 9, which equals 18. Well, this is a lot larger than 2, so we did something wrong. Can you catch the error? So, in our last Catch the Error video, we did something wrong and did not find the real global extreme values of our function. I will give you a hint. We forgot something in our plan of action. To see what went wrong, we sketched the graph of f of x equals x cubed minus 3 times x on minus 3 to 3. From this picture, we immediately see the problem. We forgot the boundary points. We can clearly see that the function has its global extreme values at the boundary. The extreme values that we found are only local extremes. So remember, when you try to determine extreme values of a function, sketch the graph to get an idea what the function looks like. And extreme values can occur at critical points, but also at boundary points. And don't forget the singular points.
Hello, we're almost finished with week 5. To help you, we will summarize this week's content. At the beginning of week 5, we wanted to determine the slope of the roller coaster track and the speed of the cart. To do so, we started by defining the derivative. The setting was as follows. Suppose a function f is given. If you move from point A on the horizontal axis to a plus delta x, the function value changes. The quotient of the vertical change and the horizontal change is called the difference quotient. It can be interpreted as the slope of the green line. Now, take delta x to 0. If the limit of the difference quotient exists, it's called the derivative of f at a. It is denoted by f prime of a or df over dx of a. The green line approaches a limiting position. This is the tangent line to the graph at point P. To determine the derivatives of more complicated functions, we first take a look at the derivatives of the standard functions. You should remember the derivatives of power functions, exponential functions, and the logarithm. We also found the derivatives of sine of x and cosine of x. The derivative of sine of x equals plus cosine of x, and the derivative of cosine of x equals minus sine of x. And in the exercises, we found that the derivative of the tangent of x equals 1 divided by the cosine of x squared. So far are standard derivatives. Now let's look at the rules to calculate the derivatives of combinations of standard functions. The derivative of a constant times a function equals the constant times the derivative of the function. The derivative of f plus g equals the derivative of f plus the derivative of g. This is the sum rule for differentiation. We also know the product rule. This rule states that the derivative of fx times gx equals f prime of x times gx plus g prime x times fx. Furthermore, the chain rule tells us that f of gx equals the derivative of f at value gx times the derivative of g at value x. Finally, the derivative of f divided by g can be calculated using the quotient rule, but remember that you can also derive it by using a combination of the chain rule and the product rule. So these were all of our rules. You should note that derivatives do not always exist. This might happen for several reasons. Some example of instances where a function f is not differentiable at a occur when f is not continuous at a, the graph of f has a kink at a, or the graph of f has a vertical tangent line at a. There are even more exotic examples, but you will not encounter those often. Finally, we looked at how to determine local extrema of a function. The most important result is the following. If a function f attains a local maximum or minimum at axis a, then either the derivative of f in a equals 0, f is not differentiable at x equals a, or the point a is a boundary point of the domain of f. The point where the derivative of f equals 0 are called critical points. Points where the derivative does not exist are called singular points. And if a point at the boundary of the domain, we call it boundary point. To find the maximum or minimum of f, you must check all 3 points. This was all the theory about differentiation. If something from this summary is not completely clear to you, you can go back to the video explaining that part. Good luck with this week's exercises.
Hi there. This week you practice differentiation of functions and you might wonder where derivatives can be used. Well, one of the main applications of derivatives is in differential equations. Suppose I want to describe the temperature of the coffee in this cup as a function of time. What do we know about this function? Well, we know that if the coffee is very hot, it cools down fast. And if the temperature of the coffee is just above room temperature, it cools down at a slow rate. So it seems reasonable to assume that the rate of cooling is proportional to the difference of the temperature of the coffee and the room temperature. This is, of course, just a simplification of the real situation, but it actually turns out to be quite accurate. Okay, let's try to put this into a formula. Let f of t be a function describing the difference at time t between the coffee temperature and the room temperature. This is the function we want to find. Then the rate of cooling is the derivative of f. This is proportional to f itself, so there is a constant k such that the derivative of f at time t is equal to k times f of t. We don't know the value of k, however, it should be negative because the difference in temperature gets smaller in time. So let's just say that k is equal to -2. Now we have obtained the relation f prime of t is equal to -2 times f of t. This is an example of a differential equation, that is, an equation that expresses a relationship between an unknown function and its derivatives. Differential equations play a very important role in, for instance, physics and engineering. Usually, these differential equations are more difficult than the one we just derived. Okay, back to our differential equation. We want to find a function f such that the derivative is -2 times the function itself. We know such a function, it's an exponential function. So we have f of t is equal to e to the power -2t. We can check the derivative of this function is -2 times e to the power -2t, which is equal to -2 of f of t. So we have obtained a solution for our differential equation. But wait, is this the only solution? No, it's not. We can take f of t equal to a constant times e to the power -2t. So we have a constant times e to the power -2t, and now we can check the derivative again. F prime of t is -2 times, and here we also get a c, times e to the power -2t. This here is exactly f of t again, so we get -2 times f of t. So we have infinitely many solutions, c times e to the power -2t for any constant c. We don't expect to find infinitely many different functions that all describe the temperature of my coffee. So what is the value of c in this case? Well, our coffee machine produces coffee with a temperature of 80 degrees Celsius. If the room temperature is 20 degrees, then the difference is 80 minus 20 is equal to 60 degrees. So at t is 0, the value of f should be 60. So what do we get in this case? Well, we have f of t is c times e to the power -2t. So f0 must be equal to 60. This is c times e to the power -2 times 0. This must be 60. So we have c is equal to 60. And the solution of our differential equation becomes f of t is 60 times e to the power -2t. Okay, so the function f describing the difference between the temperature of the coffee and the room is given by the function we have over here. So we found the function that we wanted by solving the differential equation. Differential equations are very powerful tools. They are used to model, for example, traffic flows, acoustic waves, and they are also used in financial models. You will encounter more differential equations at the university, and your knowledge of differentiation is essential to understanding differential equations.
Sustainable energy is a major theme in engineering. We want to reduce energy consumption but maintain the quality of life. This is a great challenge for science and engineering. Prêt à loger is French for ready to be lived in. It is also the name of a team students and staff of the Delft University of Technology taking part in the biannual Solar Decathlon competition for solar-powered houses. Instead of designing a new house, the Prêt à loger team turned an existing house into a sustainable one. This has more impact because only 2% of the Dutch population lives in a new house. The Prêt à loger team designed a modern, insulated skin. The skin covers a part of the house. It provides a climatic buffer zone and the surface needed to produce its own solar power. The energy consumption is minimized using these innovative technologies and solutions. To measure the effect of all these adaptations, it is essential to determine the electrical energy consumption of the household. But how do you do that?
It's difficult to measure energy consumption directly. You can measure the power, that is the rate at which you draw energy from the network, by measuring current and voltage of the incoming electricity. If the power is constant throughout time, then the total energy consumption during a period of time is simply the product of power and time. For example, if the power equals 0.4 kilowatt during 3 hours, the energy consumption is 1.2 kilowatt hour.
In reality, however, the power will not be constant. You switch electrical devices on and off throughout the day.
That's true. Moreover, if your house happens to be equipped with solar panels, as in the Prêt à loger example, then during midday your power usage may be significantly less than in the evening, or even be negative.
How to determine the effective power consumption in this case?
The answer is by integration. Welcome. In the video on sustainable energy, the following question was raised. If you know at any time the amount of power that you use at your home, how can you determine your daily energy consumption? In this video, I will show you how to answer this question using integration. Let's say we want to calculate the total energy consumption between time equal to A and time equal to B. If the power is constant during that interval, then the total energy consumption is simply the power P times the length of the interval, B minus A. But in general, the power will not be constant. What can we do? The idea is the following. First, divide the time interval into small subintervals, each of length delta t. Now we pretend that on every such interval the power is constant. This is of course not true, but if the subintervals are small, then at least the power will not vary too much. We can then estimate the energy consumption per subinterval. Let's zoom in on one of the subintervals to make this more precise. First, we choose a time in the interval. Let's call it t3 because we're in the third subinterval. Then we pretend that on this interval the power is constant and equal to the power at time t3. This is an approximation. The real energy consumption on this interval is then approximately equal to P of t3 times delta t. We can represent this product graphically by the area of a rectangle with base delta t and height P of t3, as shown in the picture. This we can repeat for each interval. Choose a point and approximate the energy consumption. The total energy consumption is then approximated by the sum of all contributions, PT1 times delta t plus PT2 times delta t, etc. We can use the summation sign to denote this sum more compactly. Here, n is the number of subintervals, in this case 5. The sum can be graphically represented by the total area of the rectangles. Of course, this is still an approximation. The power is not constant on every interval. But to make the approximation better, we can repeat the whole procedure for a larger number n of subintervals, each with smaller length delta t. In the limit that n goes to infinity and delta t goes to 0, we will obtain the exact energy consumption. This number also has a geometric meaning. In this case, it is the total area between the graph of the function p and the interval from a to b on the horizontal axis. This process of taking the limit of sums of smaller and smaller intervals is called integration. The sums that we wrote down to approximate the total energy consumption are called Riemann sums. They are named after their inventor, the famous 19th century mathematician Bernard Riemann. In the limit of the Riemann sums, as the size of the delta t's goes to 0, is called the integral of the function on the given interval. In this case, we can say that the total energy consumption is equal to the integral of the function pt for t ranging from t equal to a to t equal to b. We denote it as follows. The integral is denoted as a stretched s. The interval boundaries go below and above this sign, and it is followed by the function pt and ended with dt. You can think of the dt as a limit of the delta t's. This process is not limited to the context above. Let's look at a function f depending on a variable x. We wish to define the following object, the integral of f of x for x ranging from x equal to a to x equal to b. Let us run through the procedure again. First, we break up the interval into a number of subintervals of length delta x. Then we choose points with x-coordinate x1, x2, etc., one in each subinterval. These points are called sample points. Given a subdivision and the sample points, we can write the Riemann sum. The sum here represents the total area of a number of rectangles. Now we repeat this for increasing number n of intervals with decreasing length delta x. If the limit exists, independent of how we choose the sample points, then the number we obtain is by definition the integral of fx for x ranging from a to b. In this case, the number represents the area of the region between the graph and the interval from a to b on the horizontal axis. I say specifically in this case. In general, you have to be careful with this interpretation. More about that in the next video. To end, let us return to the original question: how to determine energy consumption on a given time interval, provided you know power as a function of time. The answer is, evaluate the integral of this function on the given time interval. I have to be honest here. In practice, it is often impossible to evaluate such an integral exactly. But in many cases, it suffices to have an approximation. To make such an approximation, you can use a Riemann sum. In fact, this is roughly what a digital electricity meter does. It measures the power at sample points in time and then calculates a Riemann sum to approximate the total energy consumption. What if you do want to evaluate an integral exactly? Taking the limit of Riemann sums can be very cumbersome or even impossible. Luckily, there is a way to circumvent taking limits. More about this in the following subsection. But first, let's practice with the concept. Welcome. When I ask my first year students, what does this integral mean? They usually answer, it's an area. Would this be your answer too? Then you should watch this video. It is true that in some cases, the number that you get when you evaluate an integral represents an area. Remember, for example, the function in the previous video. The Riemann sum represents the total area of a number of rectangles. If you increase the number of rectangles, they will cover the region between the graph and the horizontal axis more accurately. In the limit, the region is exactly covered. In this case, the area of the region is, in fact by definition, equal to the limit of the Riemann sum. And this limit is precisely the integral of the function over the interval. So in this case, the integral is an area. But in general, you have to be careful. Problems arise when the function becomes negative at certain points. What's the interpretation then? Let us first look at the Riemann sum. At points where the function is negative, the corresponding terms in the Riemann sum will also be negative. Therefore, the Riemann sum represents the total area of the rectangles above the axis minus the total area of the rectangles below the axis. Now take the limit to obtain the integral. The graph the horizontal axis and the lines x equal to a and x equal to b, enclose a region, and the integral represents the total area b of the part above the horizontal axis minus the area a of the part below the axis. It is referred to as the signed area of the region. You may wonder what the use of this signed area is. Indeed, if you want to paint the region, it's of no use. To know how much paint you need, you would have to know the actual area, in this case A plus B. But think again of energy consumption. We have seen that it is equal to the integral of the power as function of time. How can power consumption become negative? Well, for example, if you live in a modern house with solar panels on the roof, on a sunny day, the solar panels may produce more power than you use at that moment. The amount of power you deliver back to the electricity network is equal to the total area between the negative part of the graph and the horizontal axis. And to determine your effective power consumption, you have to subtract this from the area between the positive part of the graph and the horizontal axis. That is, your total energy consumption is equal to the signed area of the region enclosed by the graph and the interval from A to B on the horizontal axis. In fact, it is the aim of the Pret-a-Loger project that we mentioned in the context video to get this number to 0. So, let me return to the original question. What does this integral mean? The correct answer is, it is the signed area of the region enclosed by the graph, the horizontal axis, and the lines x equal to a and x equal to b. Please remember. Hi. So far, we have seen the definition of the integral as a limit of Riemann sums. Using this definition, we always have a way to determine an integral approximately. Replace it by a Riemann sum. Indeed, we can always subdivide the interval of integration, choose sample points, and calculate the corresponding Riemann sum. In fact, this principle provides a basis for numerical integration. But it will almost never produce the exact value of the integral. Moreover, it can be very tedious to actually evaluate the Riemann sum. Luckily, there is an extremely powerful tool to evaluate integrals exactly. It is called the fundamental theorem of calculus. You have probably seen it in high school. Let me recall the precise statement. Suppose we have the following: a continuous function f defined on the interval from a to b, and a function capital F, such that small f is the derivative of capital F. Then the following holds. The integral from a to b of fx dx is equal to capital F of b minus capital F of a. Any function with derivative equal to small f is called a primitive function or antiderivative of small f. Those terms can be used interchangeably. So by this theorem, integration comes down to finding a primitive function f and evaluating fb minus fa. Let me show you an application of this theorem in an example. Let us consider the integral from 1 to 2 of x squared dx. We need to find a primitive function of the square of x. That is, find a function which has x squared as derivative. Note that the following function will do. Capital F of x equal to 1/3 times x cubed. To check that this is indeed a primitive function, we calculate the derivative. F prime of x equals 1/3, and then we use the power law, times 3 times x squared. The prefactors cancel, and we are left with x squared, which is indeed our original function. The fundamental theorem of calculus tells us that the integral is equal to capital F evaluated at the upper boundary minus capital F evaluated at the lower boundary. So let me write the integral again. The integral from 1 to 2 of x squared dx. And now it is customary to use the following notation. Open with a square bracket, put the primitive function here, 1/3 times x cubed, and then put the boundaries here. This notation means precisely what I just said. take the function 1/3 times x cubed, evaluate at the upper boundary x equal to 2, evaluate at the lower boundary x equal to 1, and subtract. The advantage of this way of writing is that you can make clear what primitive function you use before you evaluate. It makes the calculation more transparent, and I advise you to do the same when you write down your own calculation. So this is equal to 1/3 times 2 cubed minus 1/3 times 1 cubed. Of course, we can simplify this. This is equal to 1/3 times 8 minus 1/3 times 1, which is equal to 7/3. And this is the final answer. This is the exact value of this integral. And it is also the exact value of this yellow region in the picture. It is approximately equal to 2.33. Let me correct that. 2.33. So the area of this yellow region is approximately equal to 2.33, which seems reasonable if you look at the picture. But what's important is that we calculated the integral exactly. If you think of it, the fundamental theorem may seem a bit strange. Roughly, it tells you that integration and differentiation are inverse operations. But if you compare the definition of differentiation to that of integration, it's really not clear at all that these are related. In a separate video, I will give an explanation why this theorem is nevertheless true. I would like to end with some remarks about primitive functions. First of all, primitive functions are never unique. Look at the example. We had a function capital F equal to 1/3 times x cubed, and a function small f equal to x squared. Small f is the derivative of capital F, so capital F is a primitive function for small f. But we can add any constant to capital F, for example 10. Let's call this new function capital G. The constant disappears after differentiation, so the derivative of capital G is again small f. So capital G is another primitive function of f. This works in general. If you have a primitive function, you can always add a constant to get another primitive function. In fact, this also works the other way around. If you have two primitive functions, capital F and capital G, of small f, then they must differ by a constant on the interval of integration. To see this, note that both capital F and capital G have small f as derivative. So the derivative of capital F minus capital G must be 0. This can only happen if f minus g is constant on the interval of integration. The important conclusion is that you have one primitive function, capital F of small f. You can find all others by simply adding an arbitrary constant. The set of all primitive functions is often denoted by an integral without boundaries, integral of fx dx. We call this an indefinite integral. For example, the integral x squared dx denotes the set of all primitive functions of x squared. To make this set explicit, we write one primitive function, for example 1/3 times x to the x cubed, plus c to indicate all the others. Don't forget the plus c, otherwise you only have one primitive function. In the exercises after this video, you can practice with the fundamental theorem and the concept of primitive functions. In the following video, I will show you why the fundamental theorem is true. Welcome back. In the previous video, you saw the fundamental theorem of calculus. Roughly, it says that integration and differentiation are inverse operations. In this video, I would like to show you why this theorem is true. Let me first show you why differentiation and integration are related. Let us consider a continuous function f that we integrate from a to b. Recall that when you integrate, you are actually calculating a signed area between a graph, the x-axis, the line x equal to a, and line x equal to b. Let's call this signed area S. Now let us make the upper boundary variable. To stress this, let's replace b by a more standard variable name. We cannot use x since it's already used in the integral, so let's use t instead. If t varies, so does the signed area, which we stress by writing s of t. My claim is the derivative of s is equal to f. So why is this? Well, if we change from t to t plus delta t, then s changes, let's say, by an amount delta s. Now delta s is precisely the area of the small strip in the picture. Let's zoom into this strip. If delta t is small, then the strip is roughly equal to a rectangle with width delta t and height f of t. So delta s is approximately equal to f of t times delta t. We can make this approximation better by taking delta t smaller. It follows that the quotient of delta s and delta t is approximately f of t. And this becomes exact if we let delta t tend to 0. The limit of delta t to 0 of the quotient is equal to f of t. Now if you remember the video on differentiation, then you see that the quotient is precisely a difference quotient for the function s, and the limit of the difference quotient is exactly the derivative of s at t. So we see the derivative of s is precisely f. Equivalently, we can say that s is a primitive function of f. This already shows that differentiation and integration are related. How does the fundamental theorem, as we phrased it, follow from this? Well, we have seen that s is a primitive function of f. Furthermore, note the following. S of a is by definition equal to the integral from a to a of f. If upper and lower boundary of an integral coincide, the integral is 0. More about that in the next subsection. S of b equals the integral from a to b of f, again by definition. Since s of a is 0, we can simply subtract and get that the integral from a to b of f equals s of b minus s of a. This is precisely the fundamental theorem for the particular primitive function s. The only thing is that the fundamental theorem holds for any primitive function. So, to end, suppose that capital F is any other primitive function of f. We have seen in the previous video that s and f must differ by a constant. So s equals f plus c. Now we can rewrite the expression that we just obtained. Replace s of a by f of a plus c, replace s of b by f of b plus c, and subtract. The c's cancel, and we are left with f of b minus f of a. To summarize, we have found that for any primitive function capital F of small f, the integral from a to b of small f is equal to capital F in b minus capital F in a. This is precisely the statement of the fundamental theorem of calculus.
Welcome. To understand calculation rules, it is good to have an example which illustrates them. As you know, speed is the derivative of distance over time. Using the fundamental theorem of calculus, it follows that distance traveled is the integral of speed as a function of time. This integral will help you understand all the rules of calculation explained in this video. Let us consider integrals with a fixed interval of integration. First, we consider what happens if we start traveling at twice the speed. Surely, the distance we cover in a given time also doubles. And if we multiply our speed by a different number, constant c, the distance traveled is multiplied by set c. Thus, we obtain the rule that the integral of a constant c times f equals c times the integral of f. Visually, we see that the height of the region under the graph is multiplied by c. So the total area is also multiplied by this c. Note that if the constant is negative, for example c equals -1, the region under the graph is reflected in the horizontal axis. Whereas the area above the horizontal axis would count positively, after multiplication by -1, the area remains the same, but as it is below the horizontal axis, we have to count this area negatively. Thus, the rule of calculation still holds in this case. Now, suppose you're walking forwards in a slowly moving train. Your total speed with respect to the ground will then be the sum of the speed of the train plus your walking speed. In a given time, how much you go forward will be the distance the train traveled plus the distance you have walked in the train towards the front of the train. That is, if f represents the speed of the train and g represents your walking speed, the integral of f plus g equals the integral of f plus the integral of g. We see that the area under the graph of f plus g equals the area under the graph of f plus the area between the graphs of f and the graph of f plus g. This latter area is a deformed version of the area under the graph of g, where at each point the area is shifted upwards by a different amount. However, these vertical shifts do not change the area, and thus the area between the graphs of f and that of f plus g equals the area under the graph of g. Once again, we see that our rule of calculation is valid. Let's now apply these two rules in combination in the following example. The integral from 1 to 2 of 4x cubed minus 3x squared. We can split the integral as the integral from 1 to 2 of 4x cubed dx plus the integral from 1 to 2 of minus 3x squared dx, which equals 4 times the integral from 1 to 2 of x cubed dx minus 3 times the integral from 1 to 2 of x squared dx. As we know that the integral of x to the n equals 1 over n plus 1 x to the n plus 1, we can use this to calculate these two integrals and obtain 4 times a quarter x to the power 4 between 1 and 2 minus 3 times a third x cubed between 1 and 2, which equals 4 times 4 minus a quarter minus 3 times 8/3 minus 1/3, which equals 4 times 15 minus 7 equals 8. These rules of calculation also work for indefinite integrals. For example, we could write directly the integral of 4x cubed minus 3x squared dx equals x to the 4th minus x cubed plus c. Finally, a word of warning. For differentiation, you learned the product rule and the chain rule for products and compositions of functions. For integrals, there are no simple rules to obtain the primitive function of f times g or of f of g of x. At university, you will learn some techniques which will help with these cases. Now, let's apply these rules of this video to calculate a few integrals.
Hi guys, you've already learned a lot about calculating integrals and you've probably practiced with them as well. Today I will show you a few useful properties of integrals. They will probably come in handy in the future. We will start with a property that's easy to remember. Say I want to calculate the integral of a function f from a to a. Well, then I would be after the area underneath the graph of f from a to a. But this turns out to be 0 for every function that we integrate. The second property is a really useful one. imagine you want to calculate the integral of a function f from a to c. Then I can take a point B somewhere in between a and c and split the region. So we get the integral of f from a to b and add that to the integral of f from b to c. If we look at the graph and visualize this, it's quite clear what's happening. We are just adding two areas to get the total area. For the last property, we take the integral from b to a for a function f, where b is larger than a. So what happens now? We are going to use our last two properties to determine that. So if we would take the integral of f from a to a, we could actually split that in an integral from a to b and add that to the integral from b to a. You know that the integral from a to a equals 0 for every function f. So these integrals should add to 0. This means that the integral from b to a is minus the integral from a to b. These properties can be used for integrals of every function. Note that if we apply the fundamental theorem of calculus on both sides, we also obtain this formula. Now I will give you an example of how to use one of these properties. This example shows you how to use these rules to calculate integrals of piecewise defined functions. We want to evaluate the integral from -1 to 2 of the absolute value of x. If you look at an integral you want to evaluate, the first thing that you will probably do is find a primitive function. But the absolute value of x does not behave the same on the whole interval. As you can see in the graph, the absolute value of x actually has two parts. If x is smaller than 0, then y equals minus x. But if x is larger than 0, then y equals x. So the primitive function of the absolute value of x is different depending on where you are in the interval. This makes calculating the integral from -1 to 2 a little bit harder. But maybe one of the properties you just saw can help us. What if we just split the integral using property 2, and we take the integral from -1 to 0 and add that to the integral from 0 to 2. Now the absolute value of x is just one simple function in each part, so we can substitute the simpler expressions we found. Whenever x is less than 0, we get minus x. And whenever x is larger than 0, we simply get x. So we take the integral from -1 to 0 of minus x and add that to the integral from 0 to 2 of plus x. Now we can find primitive functions for both expressions. So the primitive function of minus x is minus 1/2 x squared. And that of x is 1/2 x squared. And don't forget to use the right boundaries. Using the fundamental theorem of calculus, we can thus evaluate the first integral. This gives us -1/2 times 0 squared minus -1/2 times -1 squared. The primitive function in the second integral is plus 1/2 squared. Evaluating this gives us the 1/2 times 2 squared minus 1/2 times 0 squared. If we simplify this, we end up with 5/2. So in summary, you saw three properties. An integral with the same upper and lower bound equals 0 for every function. We can split the integral in multiple parts and add them. Interchanging upper and lower bounds of an integral results in adding a minus sign. We use the second property to integrate the absolute value of x. Good luck applying these properties.
Welcome. We learned there is no general rule for calculating integrals of compositions of functions. We can, however, calculate integrals with a linear function within a more complex function. For example, we can integrate the function cosine of 2x plus 5. Here, 2x plus 5 is a linear function inside the cosine. Linear functions involve scaling, that is, sending x to a multiple of x, and shifting, adding a constant. Let us consider these two operations separately. We first consider the integral of f of x plus c. The graph of f of x plus c equals the graph of f, but shifted c to the left. The integral of f of x plus c therefore equals the integral of f. But we have to be careful about the endpoints. Indeed, they have to shift by c. So we obtain that the integral from a to b of f of x plus c dx equals the integral from a plus c to b plus c of f of x dx. If we consider the graph of f of 2x, we see that we compress the graph by a factor of a half towards the y-axis. The area under the curve is thus also halved. Notice that the endpoints of the integral have been multiplied by 1/2 as well. If we call the new endpoints a and b, the old ones were therefore 2a and 2b. Thus we find that the integral from a to b of f of 2x dx equals 1/2 of the integral of 2a to 2b of f of x dx. More in general, the integral from a to b of f of cx dx equals 1 over c times the integral of ca to cb of f of x dx for any constant c. One might wonder what happens if c is negative. Well, let's consider the graph of f of minus x. This is the reflection of the graph of f of x in the y-axis. The area under the curve remains equal. However, notice that the order of the starting point and the end point have been interchanged. Thus, we have to add a factor -1 to account for this change. As a result, we find that the integral from a to b of f of minus x dx equals the integral from minus b to minus a of f of x dx, which equals minus the integral from minus a to minus b of f of x dx. Remember that this only works for linear substitutions. These rules do not allow you to calculate the derivative of functions like cosine x squared, where we plug a nonlinear function, such as x squared, into the cosine. Now, try to calculate the integral of cosine 2x plus 5 yourself.
Hi there! In this Catch the Error video, we will evaluate the following integral. The integral from -1 to 1 of 1 over x squared dx. We know that we can write 1 over x squared as x to the power -2, so we can rewrite the integral. We know that the primitive function of x to the power -2 equals minus x to the power -1. You can check this by taking the derivative of minus x to the power -1. So, by the fundamental theorem of calculus, we find that this integral is equal to minus x to the power -1 on the boundaries -1 to 1. And again, we know that x to the power -1 equals 1 over x. So we can write this as minus 1 over x between -1 and 1. So we know that minus 1 over 1. Take care of all the minuses here. You get this. This equals -1. -1. So our answer equals -2. Now you can see that this integral is negative. However, the integrand 1 over x squared is positive for all x, which implies that the integral should be positive. So the question for you is, what went wrong? Well, did you catch the error? Okay, let's see if we can understand what went wrong. We applied the fundamental theorem of calculus to evaluate this integral. But recall the precise statement. The function f should be continuous on the integration interval. Look at the graph of the function 1 over x squared. We see that this function is not continuous on the whole interval from -1 to 1. In fact, it's not even defined at x equal to 0. Therefore, we cannot just apply the fundamental theorem of calculus. Problems are caused by the fact that 1 over x squared is very large if x is close to 0. In fact, the function is unbounded on an interval containing 0. So far, we only treated integrals of continuous bounded functions. Integrals of unbounded functions, so-called improper integrals, must be treated differently. You will learn about improper integrals in the calculus courses at your university. For the moment, you should just remember that you must be very careful when integrating unbounded functions, or more generally, non-continuous functions.
Hi there. We are already at the end of week 6. To help you remember integration, we will summarize the essentials. At the start of week 6, we wanted to determine the energy consumption of a house in a certain time interval. However, we only knew function pt of the power consumption. In order to find the total energy consumed, we divide the interval into smaller intervals and pick a sample point in each interval. We could then approximate the total energy by summing the delta T times the power at each point. If we take the intervals infinitely small, we obtain the exact energy consumption. The approximating sums are called Riemann sums. Taking the limit of smaller intervals is called Riemann integration. Remember that an integral always has a geometric meaning. It is the signed area of a region between the graph of the function and the integration interval on the horizontal axis. By signed, we mean that the area of the parts below the axis should be subtracted. However, with this definition, we can only approximate the actual integral, because we can't take an infinitely small interval. Luckily for us, we can use the fundamental theorem of calculus. This theorem tells us that if we have a continuous function f on an interval from a to b, and we know that small f is a derivative function of capital F, then the integral from a to b of small f equals capital F in b minus capital F in a. This function capital F is called a primitive function of small f. Don't forget that when you find a primitive function capital F plus any constant is also a primitive function of small f. Because of this connection between differentiation and integration, we can use our list of standard derivatives to obtain some of the standard integrals. We will now walk through the rules of calculation again. Our first set of rules are about the interval of the integral. The integral from any function from a to a is always equal to 0. We can also split an integral. The integral of a function f from a to c equals the integral of f from a to b plus the integral of f from b to c. And the last rule, the integral of f from a to b equals minus the integral of f from b to a. Our second set of rules is about the function itself. The integral of f plus the integral of g equals the integral of f plus g. The integral of a constant, c times f, equals c times the integral of f. Unfortunately, none of these rules tell us how to calculate an integral of a composition of functions. In contrast to the chain rule of differentiation, we do not have such a general rule for integration. But in the case of a linear function substituted within another function, we have a few rules to help us calculate the integral. The integral of f of x plus c from a to b equals the integral of fx from a plus c to b plus c. This corresponds with a shift of the function to the right or to the left. The integral of f of c times x from a to b equals the integral of 1 over c times fx from a times c to b times c. That's all there is to integration for now. Of course, this was only a quick summary, so if you didn't entirely understand something, you should go back to the video explaining that part. Good luck applying your knowledge to the problems.
Hi. Until now, we considered functions of one variable and their integrals. We integrated the function of distance traveled over time to obtain the speed, and the function of power consumption over time to obtain the total energy consumption. A lot of functions you will encounter in real life, and therefore at university, will have more than one variable. Let us look at an example. Here we see the library of the Delft University of Technology. As you can see, it has a rather fancy shape with a roof covered with grass. It was designed by the Delft architects of Mecanoo. Suppose you were asked to build a suitable air conditioning system for this library. Then you would like to know the volume of the building. This volume can be obtained using integrals as follows. Let us assume that the floor of the building has a rectangular shape and that the shape of the roof is a graph of some function f. This function f should be a function of two variables x and y, because the graph of such a function is a surface in three-dimensional space. Now we divide the domain of this function, being the floor of the building, into rectangles and measure the height of the roof somewhere inside each rectangle. The height is the value of f at some point in such a rectangle. In this way, we get a number of boxes, and the volume of the building is approximated by the total volume of all these boxes. This is a Riemann sum for a function of two variables. If we now take the limit, such that the number of boxes tends to infinity, then we obtain the volume of the building. Here we define the so-called double integral of the function f that describes the shape of the roof. These kind of integrals are used, for instance, to calculate volumes, masses, and centers of mass. It is also possible to define integrals of functions of more than two variables. For example, the mass of a ball with a non-constant density is calculated by means of a triple integral. Similar to learning rules of calculations for integrals of functions of one variable, we will learn rules of calculations for double and triple integrals at the university. Your knowledge of integration of functions of one variable will be a good base for that.